Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Night on Earth. The air is still and the sky is moonless and dark, spangled with stars. A soft band of milky light arches overhead, the Milky Way, our galaxy seen from within. Standing here, we gaze up and out at the universe. Each pinpoint of starlight that reaches our eyes is ancient. Each carries a story across time. Light is the great messenger of the cosmos. A photon departs the surface of a distant star and journeys for years, centuries, millennia through the interstellar abyss, finally ending its voyage in the pupil of an eye or the lens of a telescope. When we catch that faint glow, we are witnessing a memory. We see the star not as it is now, but as it was long ago when that photon began its journey. The night sky is a tapestry woven of past moments. Every glimmer is a relic of history, a tiny time capsule ferrying the past into the present. Each of those ancient photons is like a message in a bottle, cast into the cosmic ocean eons ago, and only now reaching our shores. Consider the stars scattered above. The nearest, aside from our sun, shines with light that left it a few years ago. Others are so distant their light set out while ancient civilizations on Earth were rising and falling, or even before humanity existed at all. And yet, here and now, their ancient light touches us. In this way, observing the galaxy is an act of bridging time. We collect the aged light of countless suns and piece together what it tells us. Observation is a kind of gentle time travel, not moving ourselves, but receiving echoes from distant years and distant places. On the clearest nights far from city lights, the Milky Way's band is breathtaking. It spills across the sky like a luminous river. To the unaided eye, it is a faint, cloud-like glow, but through that glow, we sense depth, as if we are peering into a crowded metropolis of stars, far away. Long ago, we could only wonder what this milky band actually was. Was it a path of souls, a backbone of night, a river of milk from a goddess? Indeed, the very name Milky Way comes from an ancient Greek myth that it was formed by milk sprayed from the breast of the goddess Hera. It took the curiosity and ingenuity of observers over centuries to unravel the truth. That band is the combined light of billions of stars, too distant and faint for us to resolve individually. We came to realize we are inside a vast disk of stars, a galaxy, and that the Milky Way's shimmer is our edge-on view of that disk. Imagine Galileo in 1610, one of the first people to turn a telescope to that soft blur of the Milky Way. In his small scope, the haze resolved into countless tiny points. The Milky Way was not a celestial cloud or fluid. It was composed of uncountable stars. This was a revelation, our first glimpse into the true nature of our galaxy. Later, astronomers mapping the sky noticed that those stars thickened in one particular direction, hinting that the center of this starry system lay somewhere behind the constellations of Sagittarius and Scorpius. Slowly, a picture formed in human understanding. We live within a flattened congregation of stars, like a great starry whirlpool. Our sun is but one star among many in this cosmic ocean. Now, as we stand under the stars, we appreciate something profound. We are inside the very structure we are trying to understand. Any map we make of the galaxy must be assembled from our viewpoint embedded within it. It's as if we are trying to discern the shape of a vast forest while being deep among the trees, or like attempting to read an enormous book while standing on one of its pages. We cannot step outside the Milky Way to see it whole. We must infer its form through careful observation and imagination. And so, we observe. We watch the heavens with every tool we can craft, collecting light in all its forms. We gather photons like alchemists, gathering whispers of truth. Each telescope, each detector, is an extension of our eyes, allowing us to see a bit farther, a bit clearer, or in types of light invisible to our eyes. With patience and ingenuity, we learn to decode the messages that light carries, the subtle shifts, colors, and timings that reveal distances, motions, and compositions. From tiny clues, we begin to perceive the grand structure that we inhabit. Think of the sky above as a grand mosaic. Each star's light is one tile in that mosaic. By studying those tiles closely, their color, their brightness, their position and movement, we start to discern the larger image they form. We realize that the faint band of the Milky Way is not uniform after all. It has structure. Brighter patches within it appear as soft, luminous swells, which we now know to be star clouds, densely packed regions of stars in our spiral arms. Dark gaps and notches, such as the Great Rift splitting the Milky Way in the summer sky, are not empty of stars at all, but shrouded by intervening dust clouds that block their light, creating black silhouettes against the glowing backdrop. Even our naked eye view hints at the galaxy's form. We see a bulging brightness toward one end of the band, toward the constellation Sagittarius, the direction of the galactic center, and a tapering, thinner glow extending around the sky toward the opposite end, the galactic anticenter in Auriga. The peoples of the southern hemisphere, for example, saw dark constellations in those dusty rifts, an emu in the sky, a great coal sack. Our ancestors spun tales of this band of light. Today, we understand it as the plane of our galaxy's disk, full of stars and shadowed by dust. As we drink in this sight, we find it humbling and wondrous. We are looking at our galaxy from the inside, using shards of ancient light to guide us. In that gentle glow lies everything: the collected radiance of distant suns, the imprint of interstellar clouds, the secrets of our galaxy's architecture waiting to be teased out. The journey to comprehend it is only beginning as we stand here, eyes upward and hearts open to the stellar chorus of light and time. But looking is only the first step. To truly understand this galaxy we call home, we need to measure and map it. How can we gauge the distance to those countless stars? How do we chart a landscape so vast while confined to a single speck within it? Over time, we learned to coax more information from the starlight, turning observation into a precise language. One of our earliest triumphs was discovering the method of parallax, the same effect you notice if you hold out your hand and close one eye, then the other, watching your finger seem to jump against far background objects. Our Earth, in its orbit around the Sun, provides a baseline 300 million kilometers wide. Every 6 months, as we stand on opposite sides of the Sun, nearby stars appear to shift slightly against the far background. It's a tiny, subtle wobble, imperceptible to the unaided eye, but with careful instruments we can measure it. By this minuscule celestial geometry, we determine how far away those stars are. The closer a star, the more it appears to shift. For the first time, the vast void between stars had a measurable scale. We learned that even the nearest stars are tens of trillions of kilometers away, billions of times farther than any voyage our species has ever taken, and more distant ones, hundreds or thousands of times farther still. The galaxy opened up in 3 dimensions, depth unfolding from what once was a flat panorama of lights. Imagine watching a particular nearby star through the year. In January, it's aligned just so with some distant background galaxy. By July, it has traced a tiny loop in the sky. That loop is the imprint of Earth's journey around the Sun, reflected in the heavens. From that trace, we triangulate the star's distance, like a surveyor mapping unseen lands from 2 vantage points. These measurements, painstaking at first, have now become an exquisite survey on a grand scale. Today, satellites with sharp electronic eyes measure parallaxes for over 1 billion stars, pinpointing their positions in space. With this technique, our stellar maps gained reliable depth. We began to know where we are and where other stars are in relation to us. Not just their direction, but their true distance in light years. Distance alone, however, is only part of the story that light can tell. The stars have motions of their own. They are not fixed jewels set in the firmament, but travelers orbiting the galactic center, each on its long journey around. Seen from our moving Earth, their motions across the sky are subtle and slow. But if we observe carefully over years and decades, we discern a drift. A star in the Big Dipper creeps forward. A bright neighbor slides subtly southward. Tiny changes in the constellations that over centuries will alter the sky's familiar patterns. This is proper motion, the apparent motion of stars across the sky as they sail through space. Early astronomers discovered a few nearby stars with noticeable proper motion, like Barnard's star, which moves faster across the sky than any other, about the width of the full moon every 200 years. Now, with modern detectors and long-term observations, we find that nearly every star has some motion. They are all participants in a grand dance, circling the center of the Milky Way at various speeds and angles. By measuring these motions for millions of stars, we begin to trace the currents and streams of our stellar city. We see which stars move together like school of fish, perhaps born together in long dispersed clusters. We see which stars speed along faster or slower than average, which ones are plunging toward the center or flying out toward the fringe. The patterns of movement hint at the gravitational forces shaping them, drawing the unseen outline of the galaxy's mass and structure. As we map these stellar motions, we find, for example, that our Sun and its neighbors are all streaming in roughly the same direction around the galactic core, like autumn leaves caught in a slow eddy of wind. But some stars, often those outside the main disk or high above it, move quite differently, perhaps on steeply inclined or retrograde orbits that carry them far above and below the disk plane. These are clues to the galaxy's structure and history encoded in motion. We gather them eagerly, knowing each is a piece of the puzzle. Starlight carries yet more information hidden in its delicate spectrum, the rainbow spread of its colors. When we pass a star's light through a prism or a spectrograph, we see not just a continuous band of color, but a barcode of dark lines and bright lines. These are the fingerprints of elements within the star's atmosphere. Each chemical element leaves its mark by absorbing or emitting specific wavelengths of light. By reading this stellar code, we learn the star's composition, how rich it is in heavier elements forged by previous generations of stars. We learn its temperature and hints of its age. For instance, a star rich in metals, elements heavier than helium, is likely younger, formed after earlier stars seeded the galaxy with those metals. We also find, within those spectral lines, that many are shifted slightly from where they'd be if the star were at rest. Some lines are nudged toward the blue end of the spectrum, others toward the red. This is the Doppler effect, the same phenomenon that makes a siren's pitch rise as it rushes toward you and fall as it recedes. For starlight, a blue shift means the star is moving toward us. A red shift means it is moving away. Thus, the spectrum gives us the star's velocity along our line of sight, its radial velocity. Now picture this. We have parallax, giving us distance, proper motion giving us sideways movement across the sky, and spectral shifts giving us motion toward or away from us. Combine these, and for the first time, we can know a star's true motion in three-dimensional space. We can watch the galaxy's internal traffic, not just as a flat image, but as a dynamic, moving reality. With powerful surveys and observatories, astronomers have measured the velocities of millions of stars, compiling a vast catalogue of stellar motions. It is as if we have surveyed a great flock of birds in flight and traced each bird's path through the sky. From within, we map the Milky Way, not as a static snapshot, but as a living system, stars orbiting in the common gravitational field we all share. Each piece of data, a distance, a proper motion, a spectral signature, is a thread. Woven together, those threads create a rich tapestry, a model of our galaxy as it is, and, in a way, as it was, since even the motions of stars carry information about past events and the galaxy's evolution. We see, for instance, groups of stars moving in unison, perhaps born together in the same long-ago star cluster that has since dispersed, their common motion betraying their kinship across space. We find stars speeding unusually fast or slow for their location, hinting at gravitational perturbations or past encounters that have stirred the pot of the galaxy. Yet, even with such data in hand, mapping our galaxy from within remains an exercise in inference and imagination. There are still vast areas veiled to us, distances too great for parallax to reach directly, motions too subtle to detect within a human lifetime. We calibrate and extend our reach by using standard candles, special objects of known luminosity, such as certain variable stars or stellar explosions, which allow us to gauge distance by how faint they appear. We extend our velocity map by measuring not just individual stars, but also the bulk motion of star clusters and gas clouds. We are like explorers mapping a continent by combining local surveys, careful to stitch them into a coherent whole. It's a formidable challenge, but bit by bit, the dimensions of our Milky Way are coming into focus. Consider what we have learned through these patient endeavors. We know the Sun lies about 26,000 light-years from the galactic center, roughly halfway out along the Milky Way's radius. We know our galaxy is a rotating disk because we can sense the systematic motion of stars around the center. For example, stars on the inner side of the Sun, towards Sagittarius, are, on average, coming toward us, blue-shifted, as they overtake us on the inside track, while those on the outer side, toward Auriga, are receding, red-shifted, as we move away from them, indicating the entire disk spins. We know the scale of this rotation. The Sun and its neighbors are hurtling along at roughly 220 kilometers per second on this colossal circuit. Even at that immense speed, one full orbit around the galaxy, a galactic year, takes on the order of 200 million years. Our Sun has made only about 20 such orbits in its 4.5 billion year lifetime. When last it was in this same position in its orbit, the first dinosaurs were emerging on Earth, and the continents had a different arrangement. On its next pass, 200 million years from now, who knows what life, or what changes on Earth, will see the galaxy from our Sun's vantage. To put this in perspective, if the Milky Way's rotation was sped up so that one galactic year lasted a single human day, then all of recorded human history would flash by in just a fraction of a second. Our lives are impossibly brief compared to the immense cycles of the galaxy. As we enrich our map with measurements, we also engage in an act of imagination. We convert data points into a mental journey. Let us embark on that journey now, to envision the Milky Way from our local neighborhood outward, using all we have learned. Through careful observation, we have gathered enough clues to sketch the grand design of our home galaxy. It is time to leave our little perch near the Sun and travel, in our minds, across the vast expanse of the Milky Way, guided by the light and motions we have collected, like navigators following a cosmic compass. Our journey begins in the quiet suburb of the galaxy where the Sun resides. Here, roughly halfway between center and edge, the stars are relatively sparse. We are in a minor spur or branch of a spiral arm. Not one of the Milky Way's big arms, but a smaller local lane of stars and nebulae. This feature is sometimes called the Orion Spur, our local side street off a major arm. Drifting outward from the Sun, we soon encounter one of the great spiral arms proper, the vast curving streams of stars and gas that wind around the galaxy. It looms ahead like a bright cloud on the cosmic horizon, a tremendous glowing avenue in space, studded with clusters of brilliant blue stars and embroidered with luminous nebula. In these nebulae, immense clouds of gas and dust, new stars are being born. We pass by a stellar nursery where hot, newborn stars light up the surrounding gas in pink and lavender hues. Nearby, a tight cluster of young stars shines brightly, their ultraviolet light causing the remaining gas of their parent cloud to fluoresce. This is the vibrant realm of the spiral arms, where star formation continually renews the galaxy. These spiral arms are the most striking features of the galactic disk. They wind outward from the center in a graceful spiral pattern, like the swirls of a giant pinwheel. Each arm is not a solid structure, but a kind of density wave, a traveling traffic jam of stars and gas. As this wave moves through the galactic disk, it compresses gas clouds and triggers star formation, leaving a wake of bright young stars that outline the arm's shape. We see these arms as glittering, starry ribbons. Along them live massive, short-lived stars that burn hot and blue and die young, so they never stray far from their birthplaces, thus tracing the spiral pattern in glowing neon blues. Meanwhile, older stars, like yellow suns and ruddy red dwarfs, are found everywhere, even between the arms, but they are dimmer and do not stand out as boldly to our eyes. Our own sun, a middle-aged yellow star, drifts in a quieter region between two major spiral arms, essentially in the galactic suburbs, far from any bustling stellar metropolis. We are situated between the nearby Sagittarius Carina arm, closer to the center, and the Perseus arm, toward the outer galaxy, in a calmer spur that branches between them. Generations of stars have come and gone here, long after the grand spiral pattern was established. As we continue our journey through the disk, we notice that it is indeed a disk, a relatively thin plane compared to its vast width. The Milky Way's disk is often likened to a cosmic frisbee or pancake, about 100,000 light-years across but only a few thousand light-years thick. In fact, the part of the disk where star formation actively occurs, the thin disk, might be only 300 to 500 light-years in thickness in the solar neighborhood, thicker toward the center. This thin disk is where most of the interstellar gas resides, where spiral arms shape the cosmic traffic, and where bright young star clusters light up the scene. It is flat because, as our galaxy rotates and evolved, collisions and angular momentum caused most matter to settle into this plane. Let's rise gently a bit above this cosmic plane to gain perspective. From just above the disk, looking down at a slight angle, the Milky Way's layout becomes apparent. We see that the Milky Way isn't just a single flat disk of stars, but has layers and structures. Above and below the bright thin disk, there is a sparser, thicker distribution of stars, appropriately called the thick disk. The thick disk consists of older stars with fewer heavy elements, spread over a greater range of heights above and below the plane. These stars move on orbits that are inclined relative to the plane and have a wider variety of paths than the stars of the thin disk. The thick disk doesn't contain the bright gas clouds or young clusters that define the spiral arms. It is more like a fossil record of an earlier epoch of our galaxy, or perhaps the result of an ancient merger that puffed up the stellar distribution. Its presence gives the Milky Way a faint extended glow when viewed edge-on, a kind of dim, broad corona of stars, through which the brighter thin disk is threaded. Returning to the plane, we journey further inward toward the galactic center. As we travel deeper toward the core, the stars around us multiply and crowd together. The sky grows richer with starlight. By the time we are halfway to the center, the star density is noticeably higher than in our neighborhood. We pass through another spiral arm, the Sagittarius arm, packed with stellar nurseries and clusters. Here, we see the remains of titanic stars that have lived and died. For example, a great supernova remnant, an expanding shell of gas from an exploded star, its filamentary tendrils glowing with the energy of the blast. Such remnants dot the interstellar space here, markers of past star deaths. The interstellar medium grows denser and more turbulent. Radio telescopes mapping this region reveal complex networks of cold hydrogen gas and molecular clouds, gathering like thunderstorms in the distance, awaiting the next trigger to form new stars. Moving nearer to the core, the spiral arms begin to converge and blend into a continuous luminous mass. the distinction between individual arms blurs in a flood of starlight. We are entering the central bulge of the galaxy. This bulge is a huge, rugby ball-shaped or peanut-shaped concentration of stars at the galaxy's center. Here, the average age of stars increases. Many are old, swollen red giants that have shone for billions of years. The light takes on a warmer, reddish tint, dominated by these cooler old stars, and the interstellar gas is scarce. Most of it was long ago converted into stars or cleared out by supernova. In the bulge, stars are so numerous that the night sky from a planet deep in the bulge would be ablaze with thousands of stars visible to the naked eye, far brighter and more numerous than the sky we know. It would never get truly dark. When we observe the Milky Way's central bulge from Earth's skies, we are looking at this crowded hub from 26,000 light-years away, seeing it through dust that dims and reddens its light. The very heart of the Milky Way is a crowded, dynamic place. In addition to the swarming stars, there are mysterious radio sources, X-ray flashes, and high-energy phenomena. At the exact center lies something both invisible and immensely powerful, a supermassive black hole around which the entire galaxy revolves. We call this central dark object a black hole, but we might also think of it as the gravitational heart of the Milky Way. We have detected it indirectly by watching stars orbiting at fantastic speeds around an apparently empty spot in the bulge. Indeed, over decades, astronomers watched individual stars near the galactic center loop around this invisible point. One star completed a full oval-shaped orbit in just 16 years, reaching a mind-boggling velocity of over 5,000 kilometers per second at its closest swing by the unseen mass. These observations allowed us to pin down the mass of the hidden object, about 4 million suns, confirming that nothing but a black hole could concentrate so much mass in so tiny a space. Occasionally, this dark giant announces itself. If a stray cloud of gas wanders too close, the black hole's gravity rips it apart, and the infalling gas heats up and emits powerful X-rays before vanishing. For the most part, however, our galaxy's central black hole is quiet, a sleeping titan. In 2022, this inference was dramatically confirmed when astronomers captured a direct image of the region just outside the black hole's event horizon using a global network of radio telescopes. The result was a telltale ring of light, radiation from superheated gas orbiting the black hole, surrounding a dark shadow. For the first time, we saw the shadow of our galaxy's black hole, a sight that would have been unimaginable not long ago. What would it be like right next to that heart of darkness? If we could safely drift in the innermost region, we might see the fabric of space itself being warped by the black hole's gravity. We wouldn't see the black hole itself, it would be a void, but we might observe stars whipping around it in tight orbits and flashes as doomed material falls in. Around the black hole, within a few light years, is a nuclear star cluster, a densely packed cluster of stars orbiting furiously. Some of these stars are young and massive, paradoxically forming in the fierce environment near the black hole. How they came to be there is still debated. Perhaps their birth was triggered by the compression of gas streaming into the center. This cluster, along with the black hole, forms the dynamical hub of the Milky Way. If we could somehow hover above the galactic center and look down from far overhead, we would also notice that the Milky Way has a long, bar-shaped concentration of stars, stretching across its central region. Our galaxy, as it turns out, is a barred spiral. The central bulge is slightly elongated into a bar that extends on either side of the center for a few thousand light years. The bar rotates slowly, and it acts like a gravitational funnel, channeling gas from the outer galaxy inward along its sides. The spiral arms of the Milky Way actually emanate from the ends of this bar, rather than directly from a circular bulge. The existence of the bar was discovered through infrared observations, since the bar's stars are often hidden behind dust in visible light. In the tumult of the inner galaxy, the bar is another piece of the puzzle, a structural backbone supporting the inner spiral pattern. Gas flows inward along the bar and collects near the center, where it can fuel bursts of star formation or feed the black hole. Having experienced the brilliance of the galactic core, with its tightly packed stars and mysterious dark center, let us now journey outward again, this time away from the bright plane of the galaxy. We climb above the disk, moving perpendicular to the plane of the spiral, as if riding a beam of light straight up from the central region. As we rise, the full layout of the Milky Way's structure reveals itself in our mind's eye. Below us spreads the flat disk with its winding spiral arms, a whirl of starlight patterned by dark lanes of dust. We see the central bulge as a luminous peanut-shaped glow in the middle, with the straight bar cutting through it. The spiral arms trail off from the ends of the bar, curving gracefully around the galaxy's center. From this vantage point, the grandeur of the Milky Way is unmistakable. A barred spiral galaxy, one among billions in the universe, yet special to us because it is home. The combined starlight in the disk forms a hazy, glowing lens, crossed by the intricate silhouette of dust clouds. Those dust clouds, which from within appear as dark rifts, from above trace the spiral structure, particularly prominent along the inner arms and the bar, where concentrations of gas and dust are highest. Continuing farther up and out, the bright disk begins to shrink below us, contracting to a concentrated band of light. Now the surrounding environment grows darker and more diffuse. We have entered the stellar halo of the galaxy. The halo is a roughly spherical region enveloping the Milky Way, extending far beyond the disk in every direction. It contains only a tiny fraction of the galaxy's stars, so out here space is almost empty. The stars we do encounter in the halo are often very old, solitary wanderers, perhaps one here, another dozens of light years away, in stark contrast to the bustling crowds in the disk. Yet occasionally, we come across a grand sight, a globular cluster. Imagine floating into one of these clusters. Suddenly, the star density increases immensely, and you find yourself in a ball of hundreds of thousands of stars all around you, bound together by gravity. Astronomers have discovered around 150 of these globular clusters orbiting our galaxy. In a globular cluster's core, the night sky of a planet would be carpeted with countless brilliant suns, many more and closer than the stars we see from Earth's skies. These clusters are cosmic time capsules. Their stars are extremely old and metal-poor, lacking in heavy elements. They likely formed when the galaxy itself was young, before the disk fully developed, or even in small proto-galaxies that later merged to become the Milky Way. Now these clusters orbit in the halo, following long tilted elliptical paths that carry them far above and below the galactic plane. Scattered among the halo's sparse stars and globular clusters are also traces of past galactic meals, faint streams of stars rippling through space, the remnants of dwarf galaxies shredded by the Milky Way's gravity. We might not notice them with the naked eye, but our measurements reveal coherent trails, hundreds of stars moving together along the same orbit, stretched out across tens of thousands of light years. These are the ghostly footprints of galaxies the Milky Way devoured long ago, their stars now part of our halo, still traveling in the path of their original small galaxy. One of the most prominent of these streams comes from the Sagittarius dwarf galaxy, a satellite galaxy currently being torn apart. Its stars have been pulled into a long ribbon that wraps around our galaxy like a gossamer scarf. Only recently, thanks to exquisitely precise maps of star positions and motions provided by a space observatory scanning over 1 billion stars, did this substructure become crystal clear in our data, a fossil record of a cosmic merger, finally exposed by careful archaeology of the halo. The halo, then, is not a tranquil, empty realm after all, but a graveyard of sorts. and also a nursery of history, containing the debris of ancient mergers and the oldest survivors from the Milky Way's youth. Despite how far we have come, the influence of the Milky Way extends farther still. Encompassing all of this, the disk with its stars and arms, the bulge and bar, the stellar halo with its clusters and streams, is the galactic halo of dark matter. We do not see it, but we feel it in the motions of everything bound in the galaxy. The dark matter halo is enormous and massive. If we could somehow see it, it might appear as a vast, dim sphere enveloping the visible galaxy and extending hundreds of thousands of light years out. The visible Milky Way, the stars, nebulae and clusters we can photograph, is like the bright kernel at the center of an immense, unseen cocoon of dark matter. This invisible halo holds the galaxy together with its gravity. It is as if an unseen hand holds the entire galaxy in its grasp. Without it, the outer stars and gas would not be moving as fast as they do. They would drift away, unable to remain bound to the galaxy. In fact, astronomers deduce that around 85 to 90% of the Milky Way's mass must be in this invisible form of matter, leaving only 10–15% in all the stars, gas, and dust we can see. The luminous portions of the Milky Way are truly just the tip of a cosmic iceberg. The dark matter provides the additional gravity needed to keep the galactic disk intact and the outer stars tied to the whole. In our journey, though we cannot detect this dark component directly, we are always moving within it. It surrounds and permeates our galaxy, a silent partner in its evolution. Now, in our imagination, we have traced the structure of the Milky Way from our local neighborhood out to the farthest reaches, a shining spiral disk of stars with majestic curving arms, a central bulge, crossed by a bar, housing a supermassive black hole at its core, a surrounding halo of ancient stars and globular clusters, and mysterious dark matter, and an extended spherical cloud of dark matter encompassing it all. This is the architecture of our island universe, as we understand it today, gleaned from measurements painstakingly collected from our station inside the disk. It is an awe-inspiring vision, especially knowing that just a century ago, humans did not even know for certain that our galaxy was one of many. Only in the 1920s did we confirm that the Milky Way is indeed a galaxy of a particular size and shape, and that countless other galaxies pepper the cosmos beyond our own. The Milky Way itself is now estimated to span about 100,000 light-years from end to end, containing a few 100 billion stars. Our galaxy is immense, yet it is also just one member of a much larger cosmic community. For countless generations, our view of the Milky Way was limited to that hazy band of light in the sky and the visible stars around us. It is only in the last century that we have developed the means to extend our sight beyond the visible. Radio telescopes tuning in to invisible wavelengths, infrared detectors that can peer through dust, space telescopes above the blurring atmosphere, and more. Each new technology opened a fresh window onto our galaxy. With these tools, astronomers discovered a very different Milky Way, hidden behind the one our eyes perceive. A galaxy of radio glows and infrared heat, of X-ray flashes and gamma-ray bubbles. Consider the problem of dust. Invisible light, those dark rifts and patches that stripe the Milky Way, notably the Great Rift through Cygnus and Aquila and the famous coal sack in Crux, are caused by clouds of interstellar dust blocking the light of stars behind them. These dust clouds, though accounting for only a small fraction of the Milky Way's mass, loom large to our eyes because they obscure the stellar backdrop. Along the galactic plane, dust prevents us from seeing into the far distance invisible light. It creates a zone of avoidance where optical astronomy cannot penetrate. But dust's invisibility cloak has a weakness. It is far more transparent to longer wavelength light like infrared and radio. Imagine we could switch our vision to the infrared. The night sky would transform. Those dark dust lanes that cut the Milky Way's band would begin to glow softly because the dust itself emits infrared light, having been warmed by starlight. The veil of dust thins dramatically. Stars previously hidden behind dust clouds come into view. In infrared, one can peer straight through many of the dust clouds that block optical light. The galactic center, which to human eyes is hidden behind opaque dust in Sagittarius, now blazes forth in infrared images as a crowded, brilliant hub of stars. Early infrared sky surveys, pioneered in the 1960s and 70s, and dramatically improved with space telescopes in the 1990s and 2000s, revealed the central bulge and the long bar of the Milky Way clearly for the first time, confirming what radio and star count data had hinted. We see that the bulge is full of old, cool stars, dim in visible light but bright in infrared, and that the spiral arms are dotted with warm dust clouds in star-forming regions. The entire disk emerges in infrared as a continuous ring of light encircling the sky, no longer interrupted by dark gaps, a continuous Milky Way unbroken by dust. Now, let's shift to even longer wavelengths and open our radio eyes. In radio waves, the individual stars largely vanish from view. Stars emit relatively little radio energy, but other features emerge loud and clear. One of the most important radio emissions in the galaxy comes from neutral hydrogen gas. Every hydrogen atom in interstellar space can emit a faint radio signal at a wavelength of 21 centimeters. By tuning into that frequency, astronomers in the mid-20th century effectively heard the whispers of the Milky Way's vast clouds of hydrogen. They mapped the distribution of this gas throughout the sky. What they found revolutionized our understanding. The Milky Way's disk is traced by immense spiral-patterned streams of hydrogen gas, extending far beyond where most of the stars are. By tracking the Doppler shifts of this 21-centimeter emission, astronomers could chart the rotation of the galaxy and identify its spiral arms, even on the far side of the galactic center, which no optical telescope could ever see. Through radio eyes, the Milky Way's spiral structure was drawn out in detail, including portions of arms hidden behind the bulge. The zone of avoidance that plagued optical astronomy was no obstacle to radio waves. They passed through the dust and revealed that beyond the center, the galaxy continues in symmetrical splendor. In the radio view, we also see things our eyes never could. The flicker of pulsars, rapidly spinning neutron stars, sending lighthouse-like beams of radio waves. The glow of supernova remnants, where shock waves accelerate electrons to emit radio waves as they spiral in magnetic fields, and a diffuse background hiss of radio noise permeating the galaxy, caused by a combination of free electrons moving through magnetic fields and the distant multitude of unresolved sources. The center of our galaxy, in radio wavelengths, is actually one of the brightest sources in the sky. A strong radio source, called Sagittarius A, marks the location of the central black hole and its immediate surroundings. This was how the black hole was initially inferred, before the stellar orbits and images confirmed it. In radio waves, the Milky Way appears not as a single band of light, but as a complex structure. A band of emission from the disk, visible even in daytime with the right instruments, punctuated by bright spots, supernova remnants, pulsars, star-forming complexes, and with a bright, compact source at the center, the black hole's environment. Now imagine tuning our vision to shorter wavelengths than visible, into the ultraviolet. The scene shifts once more. The ultraviolet view highlights the youngest, hottest stars and the regions of active star formation. Many of the ordinary stars and red giants that dominated the infrared now fade into darkness in UV, as they are too cool to emit much at these energies. In their place, glittering like blue-white sparks, are the massive O and B-type stars, blazing fiercely with ultraviolet light. We would also see glowing nebulae, like the Orion Nebula, under the assault of intense UV radiation from these hot stars, appearing even brighter relative to the background. The spiral arms in UV are delineated strongly by these short-lived stars and their associated HII regions, ionized gas clouds. The galactic center's old stellar population would fade in UV, making the bulge much less prominent, but any regions of recent star formation or accretion near the center would stand out. The UV view, then, is a portrait of the Milky Way's vitality, emphasizing the sites of current starbirth and the presence of the hottest young stars. If we push to even more energetic extremes, into the realm of X-rays, the Milky Way we perceive changes almost entirely. Gone is the continuous sweep of billions of normal stars. Those stars are too cool and quiescent to shine in X-rays. Instead, the X-ray sky is dominated by rarer, high-energy objects, the end states of stellar evolution and violent cosmic events. We see the ghostly shells of supernova remnants filled with million-degree gas, glowing in soft X-rays. We see binary star systems where a neutron star or black hole is accreting matter from a companion. Such systems appear as point-like X-ray sources scattered through the disk, each a tiny beacon signaling where extreme gravity is at play. The dense star cluster at the galactic center lights up in X-rays due to hot gas and perhaps many small neutron stars and white dwarfs interacting. The supermassive black hole itself, usually quiet, occasionally flares, and those flares would make it a flickering X-ray source. We also detect a diffuse X-ray glow across the sky, especially toward the center and halo, indicating extremely hot, thin gas pervading the space around the Milky Way, likely a corona of gas heated by myriad supernova explosions, forming a kind of galactic atmosphere extending far into the halo. One of the most breathtaking discoveries of the past decade comes when we peer in the gamma-ray spectrum, the most energetic form of light. In gamma rays, much of the normal galaxy disappears. What remain are the signatures of cosmic ray interactions and exotic phenomena, and looming over the center, unexpected and huge, are the Fermi bubbles, two enormous lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic plane. Discovered by the Fermi Gamma-Ray Space Telescope in 2010, these bubbles are invisible in lower-energy light, but in gamma rays they glow as gigantic balloon-like structures. Their shape and extent suggest a powerful burst from the galactic center in the relatively recent past, perhaps a few million years ago, maybe a period of intense star formation, a starburst, or an active phase of the central black hole that drove energetic outflows. The Fermi bubbles reveal that the influence of the galactic center isn't confined to the disk. It has extended far into the halo. They are like a pair of cosmic chimneys, funneling energy from the nucleus out into space. Only by looking in gamma rays did these features become apparent, reminding us that each new way of seeing can unveil an entirely new facet of reality. Each of these different eyes on the galaxy, radio, infrared, visible, ultraviolet, X-ray, and gamma ray, tells a different part of the story. Yet they all describe the same Milky Way. Layer by layer, by combining these multi-wavelength views, we assemble a richer, more complete portrait. The dark, obscuring dust that frustrated optical astronomers becomes, in the infrared, a gentle glow and a transparent window to the distant reaches. The cold hydrogen gas that is invisible to our eyes comes alive in the radio, mapping out the spiral arms even on the far side of the galaxy. The ultraviolet shows us the high-energy heartbeats of the galaxy's ongoing starbirth, while the X-ray and gamma-ray views reveal the violent endpoints and energetic feedback that shape the Milky Way, from exploding stars to feeding black holes. We also begin to utilize cosmic messengers beyond light itself. Detectors on Earth have caught fleeting blasts of neutrinos, ghostly subatomic particles, from a supernova in a nearby galaxy, and observatories are now listening for gravitational waves, ripples in space-time, that could emanate from neutron star mergers or other extreme events in our own galaxy. These new forms of seeing neutrino and gravitational wave astronomy, are still in their infancy, but they hold the promise of yet further insight into the hidden workings of the Milky Way in the future. Picture the experience of gradually shifting through these wavelengths as a kind of cosmic symphony for the senses. The Milky Way is playing multiple melodies at once. The visible light is the familiar tune, the majestic sweeping strings section full of rich harmonies, the billions of stars. The infrared adds depth, the lower woodwinds, an undercurrent revealing the warm glow of dust, and the smoother distribution of old stars behind the veil. The radio brings in the percussion, rhythmic beats from pulsars, the steady hum of hydrogen clouds, the crash of supernova remnants, outlining structure with a deep, resonant background. The ultraviolet is like a bright trumpet fanfare, highlighting the most energetic star-forming regions with its bold, high notes. The X-ray might be an electric guitar riff or a sharp violin stab, sudden, intense accents from rare, violent events. And the gamma ray is an almost unheard, ultra-high note, a subtle yet profound presence marking the galaxy's most extreme outbursts. When the entire orchestra plays together, we hear the full symphony of the Milky Way, each instrument contributing its part to a masterpiece far richer than any single wavelength alone could convey. Through multi-wavelength astronomy, the limits of our sight have been greatly extended. What once was a narrow, partial view, the Milky Way as a pale band to human eyes, is now a complex, multi-layered vision. The so-called zone of avoidance in the sky has largely been conquered. Infrared surveys reveal stars hidden behind dust. Radio surveys discover even distant galaxies lying beyond the Milky Way that were once obscured. Within our galaxy, no corner remains completely unknowable just because of dust. We have the tools to probe even the most hidden nurseries of stars. We can now map the structure of the Milky Way in its entirety, even where thick nebulae lie in the way. We can see the galactic center in its full glory behind the dust, witness starbirth sites otherwise invisible, and detect the faint echoes of past eruptions that no eye could ever see. Still, each improvement in vision often reveals new mysteries. For instance, the discovery of the Fermi bubbles in gamma rays answered the question of whether our galactic center had experienced a powerful recent outburst, but it also raised new questions. What exactly caused these bubbles? A burst of star formation blowing a galactic wind, or a period when the central black hole devoured a large amount of matter and expelled jets? Why do they appear so sharp-edged and symmetric? We also found hints of smaller, microwave-emitting bubbles closer in, and X-ray chimneys extending from the center, possibly all part of the same story. Every puzzle we solve yields new puzzles to ponder. And there remain portions of the spectrum and other messengers, neutrinos, gravitational waves, where the Milky Way has more to tell us. Yet, taken together, the information we've gathered gives us a truly spectacular understanding of our galaxy. We have learned not only what the Milky Way looks like, but how it came to be and how it is evolving. This brings us to consider the Milky Way not just as a static structure, but as a dynamic, living system with its own history, a history written in the stars. The Milky Way, magnificent and dynamic as it is today, is also very old. Its present form is the result of billions of years of evolution, a story written in the motions and compositions of its stars. Just as a geologist reads layers of rock to uncover Earth's history, or an archaeologist studies artifacts to piece together ancient civilizations, astronomers have learned to read the fossil record of our galaxy. The clues are subtle. The motions of stars, their chemical compositions, their ages, their distributions in space. By deciphering these clues, we are uncovering the Milky Way's biography, how it was built, piece by piece, from the deep past to the present. One of the most telling clues is the chemical makeup of stars. When the universe began, in the Big Bang, it consisted almost entirely of hydrogen and helium, with virtually no heavier elements, what astronomers call metals. Heavier elements like carbon, oxygen, iron, and gold were forged later in the hearts of stars and in supernova explosions. Each generation of stars enriches the cosmic material a little more with these elements. Thus, a star's metallicity, the fraction of its material that is heavy elements, serves as a kind of timestamp. An old star, born when few generations had lived and died before it, will be extremely metal poor, nearly pure hydrogen and helium. A younger star, born after billions of years of cosmic alchemy, will inherit a higher proportion of metals. Now, when we survey stars in our galaxy, we find a striking pattern. The stars in the halo and those in globular clusters are generally very metal poor. They contain only tiny traces of elements like iron or calcium, maybe 1,000th of what the Sun has. These stars are fossils of the early Milky Way. They formed at a time when the galaxy, or its precursor fragments, had just begun forming stars, when only a few supernovae had seeded the environment with heavy elements. Some of the halo's metal-poor stars are among the oldest ever found, nearly 13 billion years old, dating back to within a few hundred million years of the universe's beginning. Some are so pristine in composition that they probably formed directly from the primordial gas enriched by only the very first stars, which were themselves long since gone. In their atmospheres, we see the faint chemical echoes of those first stars. These ancient stars wander the halo, individual embers from a time when our galaxy was in its infancy. In contrast, stars in the thin disk, like our Sun, tend to have much higher metallicity. The Sun contains about 2% of its mass in elements heavier than helium. That may sound small, but it's vastly higher than the metal fraction in those halo stars. It tells us the Sun is a relatively latecomer, born around 4.6 billion years ago, in a galaxy already enriched by countless earlier stars. By then, previous generations of stars had lived and died, seeding the interstellar gas with elements that would become the iron in our blood, the calcium in our bones, the silicon in the rocks of Earth. We truly are made of this star stuff. The oxygen we breathe, the carbon in our cells, all were forged in stellar furnaces long before the Sun's birth. Each of us carries pieces of ancient stars within us. The thin disk stars, especially in the inner regions, show evidence of ongoing chemical enrichment. Even within the disk, we observe that older stars have lower metallicity and younger stars have higher. It's as if each new generation of stars inherits the ash of previous generations, the heavy elements they produced, making each successive generation a bit richer in metals. Between these extremes lies the population of the thick disk and inner halo, which often have intermediate metal content and unique chemical signatures. Many thick disk stars have an enhancement in alpha elements, like oxygen, magnesium, relative to iron, suggesting they formed rapidly from gas, enriched mostly by short-lived massive stars, which produce lots of alpha elements in supernovae, before longer-lived stars had time to add more iron. This hints that the thick disk formed in a relatively quick, dramatic episode, perhaps triggered by a violent event. All these chemical clues tie into kinematic ones, how those stars move. Halo stars, as noted, often have very elliptical or inclined or even retrograde orbits, distinguishing them from the orderly rotation of the disk. The thick disk stars do rotate in the same overall direction as the thin disk, but with a bit more randomness. Some lag behind, some lead, and they have higher vertical motions. When we examine these patterns carefully, we find evidence that the halo itself might contain substructures, remnants of smaller systems. One clear sign emerged from our trove of Gaia spacecraft data. A large number of halo stars share a common motion pattern, moving on radial orbits, going out and back in, and possessing similar metallicities. They stand out as a coherent group amidst the halo field. Astronomers now believe that about 8 to 10 billion years ago, the Milky Way had a dramatic encounter with a smaller galaxy, a merger that delivered a huge influx of stars and dark matter. This invading galaxy was torn apart by the Milky Way's gravity. Its stars were strewn into the halo on those radial orbits, and its substance likely puffed up the pre-existing thin disk of the Milky Way into a thicker disk. The evidence of that event still persists in the motions and chemical makeup of stars, sometimes poetically dubbed the Gaia sausage or Enceladus stream, names given to that distinctive clump of halo stars. Such patterns in stellar motions remained hidden until modern sky surveys provided precise velocities for so many stars. Suddenly, this ancient collision stood revealed in our data, a fossil galaxy within the Milky Way's halo. In addition to that major merger, the halo holds hints of other, smaller mergers. We have found numerous star streams, long filaments and clumps of stars sharing common velocities and trajectories. Each stream is the stretched remains of some smaller object, maybe a dwarf spheroidal galaxy or a globular cluster that ventured too close and was pulled apart. The Sagittarius stream is one example we've mentioned, the ongoing disruption of the Sagittarius dwarf galaxy. There are others, the Helmi stream, the GD1 stream, and so on, each corresponding to a different accreted system. Even some globular clusters seem to belong to certain groups associated with past mergers. For instance, a set of outer halo clusters likely came in with the Sagittarius dwarf, while another set might have been part of the hypothesized Gaia Enceladus galaxy. By charting which clusters and stars came from where, we are assembling something like a family tree of our Milky Way. Which parts were original, which were adopted or acquired over time. Even within the disk itself, the stars carry memory of the galaxy's history. There are stars in the solar neighborhood that have much lower metallicity than the Sun, yet move in the plane. Perhaps they migrated here from farther out in the disk, or are part of the thick disk population. Some stars have peculiar chemical ratios that set them apart, suggesting they might have formed in an environment outside the Milky Way, say in a dwarf galaxy, and later been assimilated. The disk, especially the outer disk, contains subtle ripples and arcs of stars that might be the result of recent perturbations. Possibly, the disk ringing like a bell after the passage of a satellite galaxy. One such feature is the Monochoros ring, a ring of stars rippling around the outer disk. It might be debris from a swallowed dwarf, or simply a wave in the disk induced by a satellite's gravity. Using all these clues, astronomers have begun to sketch the Milky Way's history. In the beginning, over 12 billion years ago, our galaxy's progenitors were likely a few smaller protogalaxies, made mostly of hydrogen, helium, and dark matter. These clumps merged early on, building a stellar halo and the first, relatively small primitive disk. Many of the globular clusters formed in this era, either within the protogalactic fragments or in the nascent Milky Way. Then, around 10 billion years ago, a significant merger, Gaia Enceladus, delivered a load of stars to the halo and possibly created the thick disk by dynamical heating. Subsequent to that, the Milky Way spent the next several billion years evolving more quiescently. Gas continued to fall in, some perhaps from intergalactic filaments, some from smaller infalling dwarfs, and the thin disk grew outward, forming stars steadily. Our galaxy's spiral pattern likely persisted and perhaps reformed at times, and a bar may have formed a few billion years ago as the central disk became unstable and elongated. Minor mergers continued. Even today, the Sagittarius dwarf galaxy is being consumed, and the large and small Magellanic Clouds, our prominent satellite galaxies, are interacting with our halo and will eventually merge as well. Through all this, star formation has cycled on and off, enriching the interstellar medium further with each generation. The Sun's birth about 4.6 billion years ago came at a relatively calm time in the Milky Way's life, long after the major mergers, in a galaxy that already had a well-defined spiral structure and plenty of heavier elements. In a sense, Our galaxy is a mosaic assembled from many pieces, some formed in-house, others acquired, and this process is ongoing. Even as we speak, the Milky Way is not done changing. It is surrounded by dozens of satellite galaxies, like the Magellanic Clouds and many ultra-faint dwarfs. Some of these will eventually merge into it. And looking to the far future, our galaxy itself is on course to merge with the Andromeda Galaxy, M31, some 4 billion years from now, an event that will drastically reshape both into a new, larger galaxy. The Milky Way's story is still unfolding, and we happen to find ourselves at a rather calm chapter in that long tale. In reading the stars and their motions, we have essentially become galactic archaeologists. We take the present evidence, the trajectories and elemental makeup of stars, and infer the past events that produce them. It's astonishing that here, on a little planet, we can piece together events that occurred 10 billion years ago and tens of thousands of light years away. And yet, piece by piece, we have done exactly that. The result is a narrative of construction and transformation. Our Milky Way grew by accretion and mergers. It has been both the cannibal and the cannibalized. It has swelled over time with the infusion of fresh material, and it continues to evolve. It remembers the violence and fireworks of its youth in the motions of old stars, and it wears the accreted stars of smaller galaxies as part of its halo, like scars or trophies. We have come far. From wondering what the Milky Way's band was in the sky, we have arrived at a point where we can describe its structure, its composition, its movement, and even its history. And perhaps, on some distant world orbiting a star on the far side of the Milky Way, there could be other beings looking up at this same band of light from their vantage point, asking similar questions. They too would face the challenge of understanding the Milky Way from within, unaware of our existence, just as we were long unaware of theirs. If such observers exist, then the mystery of our galaxy is a shared one, a grand puzzle that beckons to any creature with the will to look up and wonder. About 100 years ago, we didn't even know for certain that anything lay beyond the Milky Way. This very question was the subject of the Great Debate in 1920 between two leading astronomers, Harlow Shapley arguing that the Milky Way comprised the whole universe, Heber Curtis contending that the spiral nebulae were outside our galaxy, perhaps galaxies themselves. It was only in 1924 that Edwin Hubble measured the distance to the Andromeda Nebula and found it to be far, far beyond the Milky Way. In that moment, our perspective expanded immensely. The Milky Way was revealed to be just one of countless island universes. A large galaxy, yes, but hardly the only one. Our galaxy went from being the entirety of the cosmos to being one member of the local group, our small cluster of galaxies, similar in stature to Andromeda. Today, with modern instruments, we have even measured the mass of our galaxy and Andromeda. The Milky Way is approximately on the order of 1 trillion solar masses in total. That's 1,000 times the mass of our Sun. Though stars and gas are only about 10–15% of that. The rest is dark matter. Andromeda is of comparable mass and size, and contains perhaps 1 trillion stars to our few hundred billion. Knowing this places our galaxy in context. Not only is the Milky Way not the entire universe, it isn't even the biggest galaxy in our local neighborhood. Yet for us, the Milky Way is uniquely significant. It is home. When we gaze at that Milky Band, we are looking into the structure that made us. Our sun's existence, the heavy elements that form our planet and our bodies, the gentle environment that shelters life. All these are products of the Milky Way's long evolution. We owe our very existence to events that happened in our galaxy long before the Earth formed. Ancient supernovae that synthesized iron, for example. We are connected to the Milky Way profoundly. We are a part of it. To truly appreciate our galaxy, it helps to use more familiar analogies. To illustrate another way, Imagine the Milky Way as an enormous city of stars. The spiral arms are like brilliant avenues, lined with hot young stars that shine like neon signs, bustling with nebula where new buildings, stars, are under construction. The central bulge is a crowded downtown, full of old red giants that glow like streetlights in an ancient district. At the very center, a massive city hall, black hole, governs the motions around it. The halo forms the quiet suburbs, sparsely populated by a few old stars and clusters, far removed from the busy streets of the disk. Throughout this stellar metropolis, things are constantly changing. New structures rise, stars form, and old ones crumble, stars die. Sometimes a neighboring town, dwarf galaxy, gets absorbed into the city limits, adding its stars to our population. Yet despite all this hustle and transformation, the city of the Milky Way maintains its overall character through cosmic ages. We, living on Earth in a calm neighborhood, the Orion Spur, off one of the major arms, are citizens of this galactic city. We witness its grand traffic flow around us and participate in its story, even as we go about our humble lives. Galaxies are not static backdrops. They are active, dynamic systems. The Milky Way is an ecosystem of constant change, a cosmic forest in which stars are born, evolve, and die, enriching the soil, the interstellar medium, for the next generation. Stars form in the spiral arms, live their lives, the most massive burning out quickly, the smaller ones enduring longer, and eventually end, quietly if they are sun-like, dramatically if they are huge supergiants. When a massive star dies, it goes supernova. The explosion not only disperses heavy elements into space, but its shockwaves can jolt nearby gas clouds, possibly triggering the birth of new stars. This feedback loop, stars giving back matter and energy to the galaxy, is crucial. Through this feedback, the galaxy redistributes energy and matter and regulates its star formation. Stellar winds and supernova blasts carve bubbles in the gas, sometimes clearing out regions and halting star formation temporarily, other times compressing gas elsewhere and stimulating more star birth. It's a self-balancing act. At present, the Milky Way's star-making pace is relatively sedate. It converts only a few solar masses of gas into new stars each year on average, perhaps 1 or 2 new stars like the Sun, and a few more lower-mass stars annually. By cosmic standards, this is a gentle rate. It's enough to keep the spiral arms adorned with some bright newborns, but not so high that we burn through all our gas quickly. There are starburst galaxies in the universe forming hundreds of stars per year, blazing furiously for short periods, and then quenching when their gas is exhausted or blown out. But our Milky Way seems to prefer a steady, sustainable cadence of star formation. This moderate behavior ensures that the Milky Way's gas supply will last many billions of years to come. Over time, each generation of stars changes the composition of the galaxy's gas a little more, enriching it with heavier elements. The young stars forming now carry within them the products of countless stellar lives before them. In this way, the galaxy's chemistry evolves, the metallicity of stars increasing as the cosmic soil becomes more fertilized. Our Sun, for instance, has far more heavy elements than the first generation of stars, telling us it formed in a used, enriched medium. This ongoing enrichment will continue with future generations. Meanwhile, the whole galaxy is gravitationally interacting with its environment. Our Milky Way is orbited by dozens of satellite galaxies. Some are fairly large, the Large Magellanic Cloud, and Small Magellanic Cloud, visible to the naked eye from the southern hemisphere, each a few percent the mass of the Milky Way. Others are extremely small and faint. The ultra-faint dwarfs discovered in recent years, some of which have only a few thousand stars. These satellites move around the Milky Way, and our galaxy's gravity pulls on them, Sometimes, as we've seen, it tears them apart, like the Sagittarius dwarf. The Large and Small Magellanic Clouds, LMC and SMC, are currently close by and interacting with our halo. Their gravity may be raising tides in our disk and halo, and our gravity is stripping gas from them, producing the long Magellanic stream of gas that trails behind them. In recent years, astronomers have discovered more and more of these faint satellites. Dozens have been catalogued, and more continue to be found as our surveys improve. The Milky Way's entourage of satellites is more extensive than once thought. These interactions have effects. The LMC, for instance, with its substantial mass, around 10% of the Milky Way's mass, is tugging on our galaxy's halo and might even be shifting the center of mass slightly. It's likely contributing to the warp in our outer disk. Our disk is not perfectly flat, but bent, and the gravity of the Magellanic Clouds could be one cause of that warp. The infall of the Sagittarius dwarf seems to correlate with bursts of star formation in our disk. Indeed, some studies suggest that about 5 billion years ago, and again, about 1 billion years ago, Sagittarius's close passes perturbed our galaxy and triggered higher star formation rates, possibly even triggering the formation of our Sun around one such time. Thus, the satellites have likely influenced the Milky Way's evolution. Like dancers around a larger partner, their gravitational tugs send subtle ripples through the Milky Way's disk and halo. Our galaxy will continue to grow by merging these satellites. In the far future, as mentioned, it will experience the ultimate merger, with the Andromeda Galaxy, and likely also the Triangulum Galaxy, M33, a smaller member of our local group. In about 4 billion years, Andromeda and the Milky Way will draw together, their mutual gravity distorting both. Perhaps long tails of stars will be flung out, and over a couple of billion more years, they will coalesce into a single elliptical galaxy, sometimes dubbed Milkomeda. The night sky of Earth, if Earth is still around and life still here, would change drastically during that merger, with new patterns of stars and intense star-forming fireworks for a while. Eventually, the two spirals' identities will be lost in a new, larger galactic system. Thus, even the Milky Way is impermanent on cosmic timescales. Through all of this, one cannot help but feel a sense of narrative, a sense that the Milky Way has lived a life of its own. We, as sentient beings within it, have only just become aware of that grand story. It is a bit like coming of age and suddenly learning the history of your vast family or nation, except our nation is a galaxy 100,000 light-years wide and 13 billion years old. It took remarkable scientific sleuthing to deduce this history. It is a testament to the human mind's ability to reason and infer that we can reconstruct events so remote in time and space. Our map of the Milky Way, therefore, is not just a static picture, it's an unfolding story. It shows a current snapshot, spiral arms, bar, etc., but also contains clues of how that snapshot came to be. By studying other galaxies which we can see from the outside, we gain further insight into stages of our own. We see galaxies in various merger stages, or starburst phases, or with different proportions of components, and we realize the Milky Way likely went through similar phases, or will in the future. Our understanding of galaxy formation has, in turn, fed back to refine our model of the Milky Way. Mapping our galaxy from the inside has truly been one of humanity's great scientific achievements. Over the past century, we progressed from having only a vague idea of our place in the cosmos to having a detailed mental construct of our entire galaxy, something no one observer can ever see in full. It required meticulous data collection and clever deduction. It's as if we have mapped a vast labyrinth by walking through its corridors and feeling our way, since we cannot rise above it to see the whole. And somehow we succeeded. Mapping our galaxy from within stands as a triumph of human curiosity and intellect. Even as we gather more data and refine our models, we remain observers trapped inside the system we study. We will always be looking outward from within, and that inherently limits our perspective. There may always be features we cannot perceive directly, Perhaps some subtle pattern in the distribution of stars that is too broad to recognize from inside, or some effect that requires an external view. We compensate with ingenuity and indirect methods, but there is something profound about this limitation. We are part of the very thing we are trying to understand. It is interesting to note that while we cannot see our galaxy from outside, observers in other galaxies can. To an astronomer in the Andromeda galaxy, for example, the Milky Way would appear as a faint, elongated spiral nebula in their sky, much like Andromeda appears to us. They could capture photos of our galaxy's grand design in a way we cannot. And conversely, we see Andromeda's spiral structure clearly, while the Andromedans, if any exist, must deduce it from the inside. In a cosmic sense, we and Andromeda serve as mirrors for each other. By studying other galaxies, we've come to understand our own, and in the future, the Milky Way and Andromeda will merge and no longer be separate, their destinies entwined. In about 4 billion years, as mentioned, this merger will begin, an event that future astronomers, perhaps not human, perhaps whatever beings exist then, will witness and record. The Milky Way as we know it will evolve into something new. But those changes are far in the future. For countless generations to come, the Milky Way will remain the majestic barred spiral that cradles our sun and its planets. Our explorations have transformed that misty band in the night from a source of speculation and myth into a mapped and modeled galactic system. Yet, even as we explain it scientifically, the Milky Way has lost none of its ability to inspire awe. If anything, knowing what it truly is makes it more amazing. The simple band of light has become a vast spiral of stars in our mind's eye. The tiny points of light have become distant suns with their own worlds. The dark gaps have become nurseries holding unborn stars. The slight glow on the horizon of vision has become the memory of ancient mergers and the halo of an invisible mass. So the next time you find yourself under a truly dark sky, take a moment to let your eyes wander along the Milky Way's gentle glow. Think of all the stars hidden in that band, the clusters and nebulae, the spiral arms wrapping around, and the far-off center with its secrets. Consider the journey that light has made to reach you, and the journey we have made to understand what it means. In that quiet moment, you are connected to our galaxy in a profound way, an observer within it, aware of its vastness and complexity. Think of how many before you have stood under this same sky, seeing that milky arc and wondering what it was. Now you carry the answer to their wonder. The Milky Way is our home galaxy, breathtaking in its scale, dynamic in its story, and you are a part of it. The hazy band of light ceases to be just an appearance. It becomes a personal encounter with the cosmos, a bridge between you and the ancient, ongoing story of our galaxy. It is a reminder that even as we strive to explore and understand the universe, we are already deeply home within it, nestled among the stars of the Milky Way, forever looking out and in. Before the beginning, there was nothing. Not the nothing we know. A quiet room, an empty sky. Those are still somethings. This was a deeper void, a profound absence of anything at all. No space stretched black and empty, for space itself did not exist. No time flowed, for even time had not yet begun. There were no stars, no galaxies, no light, no darkness. There was not even the void, not even emptiness. For even a void is somewhere, and here, there was no where to speak of. It was nothing. And in this nothingness, in this silence before creation, lay a mystery, an infinite stillness pregnant with potential, poised on the cusp of existence. Yet even in this absolute nothingness, one might imagine a quiet anticipation. If silence could dream, perhaps it would dream of sound. If emptiness could yearn, perhaps it would yearn to be filled. In that abyss before time, there was no watcher to perceive it, no mind to ask questions, only a possibility, waiting, without knowing that it waited. And then, in a moment, beyond moments, it happened. From the void, a spark of unimaginable brilliance and energy burst into being. In an instant, outside the realm of time, the universe was born. One moment, there was nothing. The next, there was everything, unfolding from a single, infinitesimal point. It was not an explosion in the way you might think, for there was no pre-existing space for it to explode into. It was an unfolding, an unfurling of space and time from within, like a flower blooming in absolute darkness, a tiny point containing all that would ever be suddenly blossomed, and space-time itself began to stretch and grow. I was born. I, the universe, came into existence, carrying everything, all things, all energy, all matter, all the dimensions of space and time within me. In that first indescribable fraction of a second, I was incredibly hot, incredibly dense, and oh, so small, smaller than a proton, smaller than a grain of sand, yet containing the entirety of what would become the cosmos. All that I am now, trillions of galaxies, endless space, energy beyond measure, was crammed into a point of infinite potential. My birth was not a gentle unfolding, it was a torrent of creation. Space itself raced outward, expanding at a mind-boggling rate. In truth, even words like outward fail, for there was no pre-existing space outside of that tiny primordial speck. Space was creating itself as it expanded. In the barest instant after the beginning, I underwent a sudden, explosive growth spurt. Your scientists call it inflation, a moment when I swelled at a rate beyond comprehension. Imagine something smaller than an atom blossoming to the size of a galaxy in a sliver of a second. Faster than any speed you can fathom, faster than light itself, space unfurled, carrying energy with it. Distances between points grew so rapidly that what was once near became unimaginably far in the blink of an eye. It was as though I drew a sudden deep breath. One moment I was microscopic, the next I was astronomically vast. Every part of me rushed away from every other part. This was no ordinary expansion. It was space itself stretching, like an elastic fabric pulled taut. Had there been an observer, and there was none, they wouldn't have seen an explosion from a point outward. They would have found themselves in that point as it expanded, with every distant region racing away. Think of a balloon being blown up. Every point on its surface moves apart as the balloon grows. So it was with space during inflation, every region speeding away from every other, no center, no edge, just an ever larger space for reality to inhabit. During this wild inflationary epoch, I was almost perfectly smooth and featureless. Almost, but not entirely. Even in that near uniformity, tiny imperfections existed, like the faintest of ripples on a glassy sea. These were quantum fluctuations, minuscule, random variations, little densifications and rare factions of energy, born from the jittery uncertainty ingrained in the fabric of reality. If the early universe were a calm, glowing ball, these fluctuations were slight dimples and pimples upon its surface. Inflation took these microscopic irregularities and blew them up in size. What had been subatomic wrinkles were stretched to astronomical scales. They were unimaginably small in origin, but they would become immeasurably important. For in these seed imperfection, these whisper-light variations, lay the blueprint for everything to come. The clustering of matter into galaxies, the gathering of gas into stars. In an almost perfectly smooth newborn cosmos, these tiny fluctuations were destiny in embryo. All the while, in that first second of existence, the fundamental forces of nature were taking shape. Initially, all forces were one, merged in a high-energy unity. There was no separate gravity, or electromagnetism, or nuclear forces, just a single, unified force, elegant in its symmetry. But as I expanded and cooled just a little, this symmetry began to break. It was akin to a white light separating through a prism into a spectrum of colors. Where once there was a single radiance, now there were many hues. Gravity was the first to separate from the unity, tugging at the expanding fabric of space, announcing itself as the force that shapes the macrocosm. Next, the strong nuclear force crystallized out, destined to bind atomic nuclei together. Then the electroweak force split in two, the electromagnetic force, which would govern light, electricity, and magnetism, and the weak nuclear force, responsible for certain subtle particle transformations. What was one became many, like a single note breaking into a chord. The laws of physics as we know them were being written in those moments, set into the fabric of the young universe. The great cosmic symphony was tuning its instruments. Inflation lasted only an eye blink of time, and then it subsided as abruptly as it began. The expansion didn't stop, but it slowed to a more gentle rate. In the wake of that sudden growth, my contents, space, time, energy, were spread out and cooling. Still hot beyond imagination, but cooler than that first instant of fury. With that cooling, something profound happened. Energy began converting into matter. In that early fireball, energy and matter were two forms of the same coin, constantly changing one into the other. From the blazing energy of creation, the first particles condensed, like drops of rain precipitating from a humid air. Tiny fundamental particles, quarks, electrons, and others, popped into existence. They did not appear alone. Each particle had its mirror twin, an antiparticle. For every quark, an antiquark. For every electron, a positron. Matter and antimatter, twin sides of a coin. And when these twins met, they did what twins often do in such close quarters. They annihilated one another in a burst of light. It was a fierce and frenzied dance, particles blossoming out of energy, then colliding with their antiparticles and converting back to energy. Creation and destruction intertwined, happening everywhere, all at once. It was as if each particle had a mirror image, and when the two touched, they cancelled each other out in a flash, like a perfect reflection, disappearing when the mirror is removed. The universe was a cauldron of radiant energy, partnerships in a primal dance, annihilating each other in brilliant flashes. For a time, it seemed a stalemate, matter and antimatter created in almost equal amounts, erasing each other as fast as they appeared. But there was a tiny bias in the gears of reality, a slight preference for matter. For reasons still mysterious, for every billion matter-antimatter pairs that annihilated, one extra particle of matter survived without a partner. It was a small imbalance, 1 part in a billion, but that was enough. As the fire of those early moments raged and then began to subside, these lonely survivors became the seeds of a material universe. A nearly imperceptible excess of matter over antimatter, just a few grains of sand left on a vast beach after the tide recedes, would become everything, every star, every planet, every living being. What a fragile beginning for all the substance we find around us. But it was enough. When the fury of mutual annihilation finally settled, a soup of particles remained, mostly photons, particles of light, along with neutrinos, ghostly particles that rarely interact, and those leftover protons, neutrons, electrons, matter unpaired with antimatter, ready to form the building blocks of atoms. Time was still less than a second old, but so much had already transpired. As I continued to expand and cool, the nature of the cosmos changed. Quarks, which had been bounded only by energy, now joined together in triplets, forming the first protons and neutrons. By the time I was a mere millionth of a second old, I was a swarm of particles, quarks bound into protons and neutrons, electrons zipping through a dense plasma, neutrinos flying free, and an ocean of photons bathing everything in a blinding glow. My temperature was staggeringly high, billions upon billions of degrees. In such heat, Protons and neutrons moved at fantastic speeds, colliding frequently. And in those collisions, some stuck together. A proton and neutron fused to form deuterium, a heavy form of hydrogen. Deuterium nuclei combined to form helium. In those first minutes, about 3 minutes after it all began, I became a cosmic nuclear reactor. The entire universe was like the core of a star, forging light elements in a rush. By the time I was about 5 minutes old, this flurry of nucleosynthesis had created a primordial mix of matter, about 3/4 hydrogen nuclei and 1/4 helium nuclei, with a trace of lithium and other very light elements. The basic chemistry of the cosmos was established in those first few moments. The first fusion had happened on a universal scale, hydrogen fusing into helium, releasing energy, shaping the elemental content that would later feed the first stars. After those furious first minutes, I continued to expand and cool. The temperature, while still incredibly high, fell below the threshold needed for fusion. The nuclear reactions ceased, leaving the abundance of hydrogen and helium fixed. What remained was a hot, dense plasma, an opaque fireball of electrons, protons, helium nuclei, and photons, all intertwined in a seething dance. For thousands of years, I was just such a blazing, blinding cloud, brilliant but hidden behind its own light. Photons, particles of light, couldn't travel freely. They ricocheted off electrons and protons like a frantic crowd shoving and jostling, never getting far before bumping into someone else. The universe was brilliant, but that brilliance was trapped, scattered endlessly within. As I expanded further, the energy density of radiation, light, dropped faster than that of matter. After about 47,000 years, matter began to dominate radiation in driving my evolution. Gravity had more say than radiation pressure. Space kept stretching, and with it, the wavelengths of the photons lengthened, cooling the radiation. What was once an intense, short wavelength glare stretched into a softer glow. Millions of years passed. By the time I was a few 100,000 years old, the temperature had dropped to a few thousand degrees, cool enough for a subtle but vital change. The free electrons, which had been careening wildly, combined with protons and helium nuclei to form neutral atoms. Electrons settled into orbits around nuclei, the plasma became a gas, and suddenly, the universe underwent a transparency revolution. Before, any photon would immediately hit a charged particle and bounce off. But now, with most electrons bound into atoms, light could at last travel freely. It was as if a dense fog had lifted, or a veil had been drawn away from the face of the cosmos. In that moment, the first light that had been trapped since the dawn of time burst forth and streamed across space. The universe, which had been opaque, became clear. A great glow permeated everything, a warm, diffuse radiance shining everywhere at once. To any hypothetical observer then, though none yet existed, the sky would no longer be an intense white furnace. It would have cooled to a brilliant orange hue, like the embers of a cosmic fire spread across the heavens. And as time went on and expansion continued, that orange glow faded to red, and then, beyond red, into invisible warmth. What was left of that light after billions of years would be a faint, cold whisper of its former self. In fact, that ancient light is still around even today, stretched into microwaves, the cosmic microwave background, a soft afterglow of creation that fills the sky in every direction, testimony to those early times. So, about 380,000 years after my birth, I was a very different cosmos than at the first instant. I was vast and growing, filled with a cooling gas of hydrogen and helium, and bathed in a gentle afterglow. That afterglow light, having been released, simply traveled onward, diluting and weakening as space expanded. The once blinding brilliance had become a faint luminescence. As it stretched to longer wavelengths, visible light gave way to infrared, then to microwave. Darkness, at least to human eyes, descended for a time, the first cosmic darkness since the moment of creation. Now the stage was set for a new chapter. Gravity, which had patiently been pulling at every density fluctuation since the beginning, began to work its magic more noticeably. Remember those tiny ripples, those minuscule fluctuations in density from the era of inflation. In this new, matter-dominated era, their effects began to grow. Wherever matter was even slightly denser than average, gravity exerted a slightly stronger pull, drawing in nearby gas ever so gently. Regions that had a bit more matter attracted more matter, and thus grew even denser, while emptier regions gave up matter to their neighbors and became emptier still. Over millions of years, the once nearly uniform gas developed a texture. A cosmic web of structure started to emerge. Unseen particles of mysterious dark matter, matter that neither emits nor absorbs light, had already begun to clump as well, their gravity forming scaffolds that helped ordinary gas fall into patterns of filaments and clusters. What began as tiny density differences in the primordial fireball now manifested as great clouds and strands of gas stretching across newly forming space. It happened slowly, imperceptibly at first. For a long time, to any observer, it would have seemed that nothing was changing. The universe was just a dark expanse of cooling gas. But gravity was relentlessly pulling, gathering, sculpting. Over tens of millions of years, gas drew into titanic filaments hundreds of millions of light years long and concentrated into nodes at the intersections of those filaments. It was as if an invisible hand were sketching patterns on the blank canvas of darkness, tracing the faint blueprint left by those primordial whispers. In 3 dimensions, these filaments and nodes formed a structure akin to foam, like a sponge or a vast spiderweb, with matter lining the threads and enormous voids between. The smoothness of the young universe gave way to a delicate, lace-like structure, a cosmic web of matter. Within the densest knots of that web, proto-galaxies were forming. These were the seeds of galaxies, vast clumps of gas, mostly hydrogen, some helium, gathering under their own gravity. They were not yet the glittering star cities we know as galaxies today, for they had no stars, not yet. They were like dark, nebulous clouds, quietly accumulating mass in the cosmic night. You could have traveled for tens of thousands of light years across one and not seen a single star, only the faint glow of the residual heat and perhaps the very, very dim molecular emission of cooling gas. These proto-galactic clouds grew in mass and began to fragment into smaller, denser pockets within. Think of a giant cloud many light years across, breaking into clumps, each clump destined to become a star cluster. Inside those clumps, the first stars were about to ignite. Gravity drew gas inward, tighter and tighter. As a clump contracted, it spun faster, like a twirling skater pulling in their arms, and flattened into a disk. At the center of this disk, gas piled up, growing ever hotter and denser. Imagine an enormous cloud core, 100 times the mass of our sun, collapsing under its own weight. The temperature in the core climbed to millions of degrees. All the while, the gas was being squeezed, compressed by its own gravity, the atoms crowding closer and moving faster. There comes a moment when the pressure and temperature at the core of a collapsing cloud become so high that hydrogen nuclei begin to fuse together to form helium. And with that fusion, a vast amount of energy is released. For the first time in cosmic history, a star blazed forth. It happened in many places around roughly the same era, over a span of a few 100 million years. But we often speak of the first star as a symbol of them all. In one of those dark proto-galaxies, in a dense pocket at the center of a collapsing gas cloud, there was a sudden outpouring of light. A brilliant, blue-white radiance flooded out from that point, the dawn of starlight. The cosmos that had known only diffuse, background glow now had point sources of light, shining fiercely like new candles lit in a dark room. The cosmic dark age was ending. The cosmic dawn had arrived. The first stars were not like the stars that twinkle in our familiar night sky.
These were giants, monsters of brilliant light and short life. They were made almost entirely of hydrogen and helium, for those were the only elements the universe had at that time. Lacking heavier elements, the gas cooled less efficiently, which meant the stars that formed tended to be very massive, tens or even hundreds of times the mass of our sun. They burned hot and blue, pouring out ultraviolet light. They lived fast and died young, exhausting their central fuel in only a few million years. For comparison, a star like our sun lives about 10 billion years. These titans lived only a few million, an eye blink in cosmic terms. At first, these newborn stars were solitary beacons in enormous dark regions. But they rarely formed truly alone. Each arose from a cloud that typically made a cluster of stars. Indeed, a cluster of first stars might ignite almost simultaneously, like a burst of celestial fireworks. Within those proto-galaxies, you'd now see clusters of brilliant blue stars shining together, illuminating their surroundings. Their intense light began to transform their environment. High-energy ultraviolet photons from these stars struck the surrounding hydrogen gas that had not yet collapsed into stars, ionizing it, knocking electrons off atoms and turning the gas into plasma once more. Each star became surrounded by a growing bubble of ionized, transparent gas. These bubbles of light expanded and eventually merged with bubbles from other nearby stars, until large volumes of the proto-galaxies were cleared of opaque, neutral gas. The dark, interstellar medium within young galaxies was being turned transparent by the harsh starlight, the second time the universe had turned transparent, the first being at recombination on a cosmic scale. Now it was happening locally around stars. It was a glorious sight, where once there had been utter darkness, now pearls of starlight hung in the blackness. The proto-galaxies, those island universes of gas, were no longer dark. They sparkled with nascent star clusters. One by one, then by the thousands, stars were coming to life across the cosmos. The universe's first sunrise was not one star, but a multitude of them blinking on over time, like the first stars emerging in the twilight sky. Yet these first stars lived under a shadow of impending doom, for their very mass guaranteed that they would not last long. Within their cores, nuclear reactions raged furiously, fusing hydrogen into helium, helium into carbon, and onward to heavier elements, racing through fuel in mere millions of years. Eventually, in the heart of a massive star, iron was formed, and iron is a full stop for stellar fusion, for fusing iron does not release energy, but consumes it. Once a star's core turns to iron, the delicate balance holding the star up, outward pressure from fusion versus inward pull of gravity, shatters. And so it was that the first generation of stars met violent ends. Imagine a giant star, 30 times the mass of the sun, that has shone for 3 million years. In its final moments, its core collapses in an instant, and then, boom. The star erupts as a supernova, a titanic explosion brighter than a billion suns. One by one, many of those early stars died this way. For a brief time, each supernova outshone its entire protogalaxy. The darkness of space was punctuated by these stunning flashes. When the first star went supernova, it was not an end so much as a new beginning. In that explosive moment, the star's core imploded and then rebounded, hurling the star's outer layers, now enriched with heavy elements, outward into space. Elements like carbon, oxygen, silicon, and iron, made in the star's life and death throes, were blasted out, seeding the surrounding gas. Thus, the first stars sowed the seeds for all future complexity. They produced the first heavy elements beyond helium, the carbon that would someday compose living cells, the oxygen that would fill future skies, the silicon and iron that would build rocky planets. These elements were cast into space, mixing with primordial hydrogen and helium. The glowing wreckage of a supernova, a tangle of expanding filaments rich with new elements, formed a nebula, perhaps resembling the beautiful Crab Nebula we see today from a supernova long ago. These nebulae were the graves of the first stars and the nurseries of the second generation. In the wake of destruction, creation continued. The gas, now a bit enriched with heavier elements, began to cool and fragment more efficiently. Soon, new stars began to form from the debris-laden clouds. Generation upon generation of stars unfolded. The second generation had a different character. Thanks to heavy elements, it could include smaller mass stars, some like our Sun, which live far longer than the massive ones. Some of the second generation stars still burn today, nearly 13 billion years later, as ancient red stars in the halos of galaxies. As stars continued to form and die and form again, the proto-galaxies grew more substantial. They also interacted with one another. Gravity drew clumps of gas, proto-galaxies, together, merging them into larger structures. Two small primitive galaxies might collide and meld, their stars passing through each other's ranks like intermingling swarms of bees, their gas clouds slamming together and igniting bursts of new star formation. Slowly, the chaotic clumps merged into more organized galaxies. Some became spiral galaxies, flattened disks spinning in space, with curved arms wrapping around a central bulge of older stars. Within these spiral arms, waves of star formation lit up periodic patterns, giving the arms a frothy, luminous appearance. Other galaxies became ellipticals, more ball-shaped collections of stars, often formed from violent mergers that scrambled their stars into a diffuse, ellipsoidal swarm. Galaxies gathered into groups and clusters, bound by gravity, great societies of galaxies orbiting a common center. Those clusters linked into superclusters, forming the largest structures in the cosmos, following the threads of the cosmic web that the early fluctuations laid out. Deep in the hearts of growing galaxies, stars sometimes crowded together and collapsed in on themselves, forming bottomless wells of gravity, black holes. Some of these black holes grew supermassive, feeding voraciously on gas and even the stars around them. When they accreted matter rapidly, they blazed as quasars, beacons of unbelievable brightness shining across the universe. In time, many settled into quiescence, sitting as silent, dark giants in the galactic cores. These supermassive black holes anchored the centers of galaxies, their tremendous gravity helping to govern the orbits of stars. Every large galaxy would come to host one. Even if they were no longer actively devouring matter, their presence was felt by the whole galaxy. They were like heavy stones dropped in the center of spinning disks, influencing the motions around them. By roughly 1 billion years after the Big Bang, the universe was recognizably structured. The cosmic web glistened with galaxies along its filaments. The vast voids between were truly dark, starless expanses stretching millions of light years. Clusters of galaxies huddled in dense nodes of the web. The early universe's fireworks were largely over. Now came the long, stately age of galactic maturation. Over the next several billion years, galaxies continued to merge and grow. Spiral galaxies sometimes collided to form ellipticals. Ellipticals captured smaller dwarfs. Clusters grew larger as more galaxies fell in. The universe was dynamic and alive, a grand ecology of worlds, with gravity as the guiding force. In one quiet corner of this grand cosmic tapestry, about 9.2 billion years after my birth, roughly 4.6 billion years ago by Earth's calendar, a modest spiral galaxy was thriving. It was one among countless others, typical, with a graceful spiral structure, bands of star-filled arms, and a glowing core. In one of its spiral arms, within a giant molecular cloud enriched by previous generations of stars, something special was stirring. The cloud, dozens of light years across, began to collapse under its own gravity. It fragmented into clumps. One clump in particular drew together enough mass to form a star, much like those that had come before. But this time, this star would have a far-reaching story. As the clump collapsed, it spun faster and flattened into a swirling protoplanetary disk around a dense core. In that core, as in so many before, hydrogen fusion ignited. A new star was born. It was an average star, not particularly massive or remarkable, a yellow dwarf star. But around it, within that disk of gas and dust, planets were forming. Grains of dust, rich with elements like iron, silicon, carbon, and ice, stuck together, forming pebbles, then boulders, then mountain-sized planetesimals. These merged through countless collisions, building up into planets. Close to the star, where it was warm, only metals and rocks could solidify. Here, small rocky planets emerged. Farther out, ices and gases gathered into giant planets. One of the inner rocky spheres took shape at just the right distance from the star. It accumulated iron and silicates. It grew and cleared its orbit. In time, this young planet cooled on the surface and developed a solid crust. Comets and asteroids bombarded it, delivering water, while its own volcanoes outgassed an atmosphere. This world, under the gentle warmth of its sun, came to have oceans, vast blue oceans covering much of its surface. Our galaxy had countless planets by now, but this one would be unique. A blue gem in space, with both water and land, clouds and rain, a complex cycling of elements, a planet we now call Earth. In its infancy, Earth glowed red from constant impacts. But as ages passed, the bombardment eased, the surface solidified. Rain fell for centuries upon centuries, cooling the hot rocks, carving the first rivers, and gathering into the first seas. The air was thick with carbon dioxide and water vapor, and storms raged under a dim young sun. Lightning forked through the skies, and meteorites still occasionally pelted the surface. In the turbulent seas, enriched by minerals from below and energy from above, chemistry did something astounding. It came to life. Exactly how it happened is shrouded in mystery, one of the universe's great remaining questions. Perhaps in a warm tidal pool, or in the mineral-rich darkness around a deep-sea hydrothermal vent. Somewhere, simple molecules joined into complex chains capable of making copies of themselves. Perhaps clays or surfaces helped organize them. Perhaps a stroke of lightning fueled their assembly. But as improbable as it might have seemed, it happened. The first living organisms emerged in the young ocean. They were microscopic, much simpler than any single cell alive today, but they carried the spark of self-replication and metabolism. They could grow, divide, and evolve. With life, the universe found a new way to organize matter. Those first organisms were like tiny flickering flames in the cosmic night, fragile but tenacious. Over time, they diversified. They invented new strategies. Some learned to harness sunlight for energy, inventing photosynthesis and releasing oxygen as a byproduct, turning the sunlight falling on the ocean's surface into usable fuel. Others devoured these pioneers or their byproducts. They formed mats and colonies, gradually transforming Earth's environment. Oxygen, that reactive gas, began to fill the oceans and then the skies, changing the planet's chemistry and paving the way for more complex life. Eons passed. On the seafloor, simple cells joined together into more complex cells with nuclei. These complex cells, in turn, joined in cooperative communities, becoming the first multicellular organisms. By around 600 million years ago, the oceans teemed with simple animals, jellyfish-like creatures and wormy things. Then came the Cambrian explosion, around 540 million years ago, when an astonishing diversity of life forms blossomed, creatures with shells, exoskeletons, eyes, mouths, legs. Life was experimenting with form and function, filling every niche in the seas. Plants colonized the land, greening the continents with mosses and ferns. Not long after, bold amphibious creatures crawled out of the water onto muddy banks, taking the first breaths of open air. Forests of tall trees arose, covering the land in green canopies. Insects buzzed through ancient skies. Amphibians gave rise to reptiles that could venture farther inland, freed from the need to lay eggs in water. Dinosaurs came forth and ruled the earth for over 160 million years, evolving into myriad shapes, from gentle giants with long necks browsing treetops to fearsome predators stalking on two powerful legs. Small nocturnal mammals scurried in their shadows, and birds, bright, singing descendants of small feathered dinosaurs, took to the skies. The earth saw upheavals too. It was struck by asteroids. It shuddered with volcanic rages. It froze and thawed in long cycles of climate change. About 66 million years ago, a large asteroid, mountains in size, impacted Earth, creating a blast that darkened skies worldwide. In the ecological disaster that followed, the reign of dinosaurs, save for the birds, came to an abrupt end. But life persisted. In the void left by giants, the small and adaptable took hold. Mammals that had lived in the margins now diversified. Some remained small and rodent-like. Some returned to the seas as whales and dolphins. Some became towering mammoths and rhinos, and in certain lush corners of Earth, some primates descended from tree-dwelling ancestors began to walk upright. From one lineage of those primates came a species with an extraordinary gift, intelligence, capable of curiosity about the cosmos. These were humans. Our early human ancestors looked up at the same sun that had once been a cloud of gas, at the same moon that had been born from a collision early in Earth's history, at stars that had been shining for billions of years before their kind ever existed. They looked up in wonder. They felt small under the canopy of the night and created stories about the lights overhead. They were clever. They learned to make fire to warm the night, to fashion tools from stone and bone, to paint their dreams on cave walls. They began to ask questions. What are those points of light in the sky? How did the world begin? Human curiosity grew alongside human knowledge. Over time, they built civilizations. They charted the stars and noticed their regular movements. They gave names to constellations and planets, wove myths and gods into the tapestry of the night. Without realizing it, they were seeking connection with the cosmos, their birthplace. They observed patterns, the way the sun rises and sets, the cycling of the moon, the procession of seasons, and eventually, they sought deeper explanations. They invented science and mathematics, devising tools to measure and predict the motions of heavenly bodies. And with each discovery, they peeled back a veil of ignorance. For a long while, humans believed Earth was the center of all things, understandably, from their limited perspective. But in time, they learned that Earth is a planet orbiting a star, that their star is one among many in a great city of stars called the Milky Way, and that the Milky Way itself is but one galaxy among the immense multitude scattered through the universe. They built telescopes to extend their vision, and what a revelation those brought. They saw the moons of Jupiter, the rings of Saturn, myriad stars too faint for the naked eye, and fuzzy patches that eventually they realized were other galaxies far beyond our own. They began to truly grasp the scale of the cosmos and their place within it. They also found evidence for my story, our story. In the mid-20th century of the human calendar, two of them discovered a faint hiss of microwaves coming equally from all directions in the sky, the very afterglow of the Big Bang that I set free so many eons ago, still detectable as a whisper of heat. They had, without knowing it at first, detected the relic light from my infancy. In laboratories and observatories, humans pieced together that the lightest element's abundances matched what would be made in a hot, early universe. They saw galaxies flying apart, space expanding, as Edwin Hubble interpreted, which implied everything must once have been closer together. Bit by bit, observation by observation, the evidence mounted for what they would call the Big Bang, the very event I am describing to you now. Humans, curious and tireless, had unraveled the outlines of my story, deducing that the universe had a beginning in time and has been evolving ever since. And now, after a long journey of curiosity spanning eons, here you are, one of those inquisitive humans, listening to my tale. You stand on that small blue planet, circling a modest star in the suburbs of an ordinary galaxy, trying to fathom how it all came to be. To me, your arrival is very recent. If the entire age of the universe were compressed into a single year, all of human history would occupy only the last moments of the final day. Yet, in those fleeting moments, you have begun to comprehend the whole tale from the year's dawn to its dusk. You gaze up at the night sky, perhaps with the same wonder your distant ancestors felt, but armed with knowledge they lacked. You ask the same timeless questions. How did this all begin? What came before? What lies beyond what we can see? What is the meaning of time? These questions that echo in your mind are the very questions I have carried with me since the dawn of time. Through you, the universe, I can ponder my own existence, for I, the universe, have awakened into consciousness through your thoughts. Your eyes are my eyes. When you look into the depths of space, it is the cosmos seeing itself. Your curiosity is my curiosity. Your wonder, a facet of my own wonder at my vastness and complexity. I have grown old and vast. Over 13 billion years have passed since my fiery birth, and in that time, I have expanded into a cosmic expanse of staggering proportions. Hundreds of billions of galaxies adorn my span, each with billions of stars. From my one tiny origin, I now stretch so far that light itself, the fastest thing there is, takes billions upon billions of years to traverse my breadth. And I continue to expand, ever larger, ever more filled with possibility. It is wondrous to me that from the simplicity of that initial fireball has arisen such complexity and beauty. Out of uniformity came structure. Out of scorching plasma came the delicate forms of galaxies, stars, planets, and living beings. The journey from the first moment to now has been one of transformation, from simplicity to complexity, from chaos to meaning. Still, there are mysteries that even I, the universe, do not know. I find myself in the peculiar position of conscious ignorance. I can ask questions through you that I have not answered. What came before my beginning? I find no definite answer within myself. Perhaps before I was born, there was simply nothing at all, no time, no space, truly nothing, and my emergence was the absolute beginning. Or perhaps there was something, a prior universe that collapsed and gave birth to a new one, or an eternal landscape of universes of which mine is just one bubble. Some among you speak of a divine creator who set me into motion. Others imagine a quantum fluctuation in an eternal void. I cannot confirm or deny such speculations. The truth is veiled from me. With my birth, time was born, so the question of before may not even be meaningful. I am like an orphan with no memory of parents, if indeed any existed. The question, why is there something rather than nothing, echoes without answer. I ask, what came before the beginning? And I must answer, I do not know. What lies beyond the farthest edges of me? This too is a mystery. I expand ever outward, but do I have an outside? If you traveled in one direction forever, would you leave me or simply end up back where you started, as on a globe? Perhaps I curve in on myself. Perhaps I extend infinitely. Maybe beyond the horizon of what you can see, there are realms of space unconnected to ours, or other universes entirely separated from ours by dimensions we cannot perceive. I envision an endless ocean of universes, with our cosmos as just one foam bubble among countless others, a multiverse. But these other bubbles, if they exist, are forever out of reach. No light from them will ever reach us. To me, effectively, they do not exist.
As far as I'm concerned, I am all that is. Does that mean there is nothing beyond, or simply that I'm isolated in a greater multiverse? I cannot say. The concept of beyond the universe might be as meaningless as a fish contemplating what lies beyond the ocean. What lies beyond all I am, I do not know. And time, what is time? I know time only as the succession of events, the ticking away of moments since my birth. Time flows ever forward, entwined with the expansion of space. But why does it have an arrow? Why can we remember the past and not the future? Is time an illusion or an emergent property of consciousness? I feel time as a fundamental aspect of reality, born with me in that first moment. It moves always forward, never backward, carrying me and you from one chapter of the story to the next. But might time be part of something larger? Could it be cyclical? Will it have an end as it had a beginning? These questions baffle me as much as they baffle you. What is the true nature of time? I cannot say with certainty.
So yes, I have questions as well. What came before? What lies beyond? What is time? These grand questions linger like distant galaxies on the edge of my field of view. Faint, tantalizing, unresolved. Perhaps some answers will forever elude us, remaining secrets to keep the cosmos always a bit mysterious. Perhaps that is for the best. A little mystery, after all, adds to the wonder of it all. If everything were known, perhaps existence would lose some of its poetry. Yet, amid these cosmic uncertainties, there are truths of which I am utterly sure. Truths that shine clearly like the stars in a night sky. One is that you and I are not separate. We cannot be. You are made of me, through and through. You are made of the universe and utterly connected to it. Every atom of your being, every element in your body was forged in my history. You are a child of the cosmos in the most literal sense.
Remember the story so far. In the beginning, only hydrogen and helium existed. From them, stars were born. Those stars, in their hearts, created carbon and oxygen and iron and all the rest. And in their deaths, they scattered those enriched ashes across space. Imagine a giant star in its final moments, exploding as a supernova and casting its guts, carbon, oxygen, iron, into the void. From that chaos, specks of iron travel across the galaxy. Eons later, in a newly forming solar system, those iron atoms become part of the blood coursing through a human heart, carrying oxygen to keep it alive. Thus, the violent death of a star long ago pulses in the beat of your heart today. The very substance of your body is stardust. The hydrogen in your cells, in the water that makes up more than half of you, is ancient, born in the Big Bang itself, nearly 14 billion years ago, nurtured in the fire of creation. The carbon in your muscles, the calcium in your bones, the iron in your blood were synthesized in stellar furnaces and in the fiery throes of supernovae, billions of years past. Supernovae are the universe's great alchemists, turning lighter elements into heavier ones in the crucible of their explosion. Imagine the calcium in your bones right now. It was forged in a star that died before our sun was born. Imagine the iron atoms in your blood. Billions of years ago, they were deep in the core of a massive star. Now they travel through your veins, carrying oxygen to sustain the fire of life within you. Even the oxygen you breathe, that sustains each of your cells, was created by stars more massive than our sun, then spread through space and finally drawn into the lungs of Earth's living creatures. Your DNA contains phosphorus and nitrogen that were likewise formed in some ancient star. There is no hiding it, no denying it. You are a mosaic of the cosmos, built of pieces as old as time. You are the Big Bang, given consciousness. You are the primordial fire of creation, cooled and shaped into living form. You are starshine and interstellar dust, coalesced into awareness.
Think of the breath you draw at this very moment. As you inhale, filling your lungs, you take in oxygen atoms that might once have danced in the atmosphere of ancient Earth, or been part of a water molecule in some dinosaur's blood, or drifted in the far past as part of a carbon dioxide molecule exhaled by a Cambrian fern. Trace those oxygen atoms back, and you find they were forged in a star's core, long before our planet existed. With each breath, you partake in a cycle as old as time. Atoms created in the infancy of the universe, cycled through stars and space and air, now entering your body to keep you alive. When you exhale, you return some of those atoms back to the world. Perhaps a carbon dioxide molecule you release will be taken up by a plant and become part of a leaf, continuing the grand circulation of matter. Your breathing echoes the first fusion fires of the young cosmos and the later fusion in stellar hearts. Inhale, exhale, the universe breathing in and out through you. Think of the universe as a living body. Galaxies are its organs, stars its cells, and each conscious being like you is a nerve ending through which it feels and knows itself. We are the universe, experiencing itself in myriad forms. Through your senses, I, the cosmos, perceive my beauty. Through your curiosity, I investigate my own nature. When you look at a galaxy through a telescope, it is the universe seeing its own ancient image. Light that left that galaxy millions of years ago finally reaching its eyes, your eyes. When you marvel at the intricacy of a flower or the anatomy of a bird, it is the universe marveling at the structures it has brought forth. You are a way for me to know myself. You and I, we are not separate. We have never been separate. It's not just that you are made of stardust and shaped by physical laws. More profoundly, you are an expression of the universe, one facet of its ongoing story. The cosmic evolution that unfolded over billions of years flows through your veins and lives in your genes. Consider this: the same processes that gave birth to galaxies and stars eventually gave birth to you. You are an expression of the cosmos that can think, feel, and reflect on itself. We are bound together by this continuity. We often speak of the Big Bang as an event long past, but in a sense, the Big Bang is still happening. Its aftermath is ongoing, and we are part of it. The initial outward rush of space continues in the expansion of the universe today. The cooling and the clustering of matter continues as galaxies form new stars, and those stars give light and life to new worlds. And within you, the energy of that explosive birth still sings. In the warmth of your body, a distant echo of the primeval heat. In the spark of electrical impulses in your nerves, driven by chemical gradients that ultimately trace back to nuclear reactions in stars, powered by the Big Bang's initial energy. The Big Bang lives on as the cosmic background glow, and also in every living being that carries out the legacy of those first particles and forces. Remember this: you are not an outsider looking in on the universe. You are an integral piece of it, an active participant in its cosmic drama. The story of the Big Bang is your story. It's the story of everything that ever was, and that includes you. When you peer into the night and feel small, recall that you are also immensely large in a way. Inside of you are trillions of cells, each a tiny universe of molecules. And within each molecule are atoms that were forged in stellar cores or in the Big Bang itself. You are vast within, and your inner complexity mirrors the outer cosmos. The iron in your blood ties you to the death of a star. The water in your cells ties you to the clouds of the early universe. The photons hitting your retinas at this very moment, letting you read and understand, may have been on a journey for millions of years from a distant star, only to end their long voyage by triggering an image in your mind. In a very real sense, when you learn about the cosmos, the universe is learning about itself. I began this tale in silence and nothingness. Now there is sound and life and mind. Through billions of years, I, the universe, have become self-aware in you. Feel that profound connection. Let it fill you with humility and reverence, but also with a sense of belonging. The very atoms that compose you were there at the beginning, and they will be part of the universe long after you are gone. We are threads in the tapestry that began at the Big Bang and continues to be woven with each passing moment. The saga of the cosmos is far from over. Stars are still being born and still dying in brilliant supernovae. New planets are coalescing in disks around young stars. Perhaps on some of those worlds, life will spark or is even now burgeoning, and maybe new minds will one day gaze at their skies with wonder as you do at yours. The universe is always changing, always moving, and we, with our brief lives, are part of the grand change. So, when you feel alone or insignificant under the vast stars, remember, you are significant. You are the universe, as much as any galaxy, as much as any star. You are the cosmos made conscious, a fragment of the sky that knows itself. Your heartbeat echoes the first vibrations of the Big Bang. Your breath echoes the expansion of space. Your gaze into the night is the universe contemplating its own existence. From the silence before time to the symphony of the present, we have traveled together. The hydrogen that appeared in the first second now courses in your blood as part of H2O, and the light first released in that primordial fire now gently warms the space between galaxies at just a few degrees above absolute zero. The universe remembers its origins, not just in background radiation and in drifting atoms, but in you. You carry within you the memory of stars and the memory of that first brilliant moment of creation. Our journey from nothingness to structure, from the void to the vast, has been almost 13.8 billion years long and counting, and it continues. With every second that ticks by, new stars ignite, space stretches a little more, and life, at least here on Earth, lives out its complex dance. We, together, are the product of the Big Bang, and also the chroniclers of it. The tale I've told is drawn from evidence gathered by curious minds, yours among them perhaps. And in telling it, the universe is recounting its autobiography through a human voice. Now, as I finish this story, take a moment to reflect on what it means. Feel the gravity of it. Not just the literal gravity that holds you to Earth, but the gravity of understanding. You are connected to the first light that ever shone. You carry pieces of the first stars in your body. Your existence was enabled by an unbroken chain of events tracing back to that singular creation event. In a fundamental sense, you are the Big Bang, billions of years later made flesh. You are the universe's memory, its awareness, its poetry. When you look up at the glittering sky tonight, perhaps you'll see it differently. The Milky Way, arching overhead, is not just a random scattering of stars. It's the luminous spine of the galaxy we call home, itself a product of cosmic evolution and containing stars that contributed matter to make you. The gentle glow you may see on a very dark night, a faint band of light, is partly the blended light of distant stars, and partly the faint memory of the fireball of creation, still with us. The starlight that strokes your eyes is a message across time and space, a reminder that we are all part of one story, the same story. This story, my story, our story, will continue to unfold. And we, me, the cosmos, and you, the listener, are in it together. Every day, new questions will arise, new discoveries will be made. Perhaps one day, far in the future, some of those big unanswered questions will find answers. Or maybe not, and the mystery will deepen. There will always be new wonder. But whatever happens, one thing remains true. We are inextricably one. I began in silence and mystery. Now I speak through your voice and your understanding. I began as a single point. Now I am vast beyond comprehension and filled with stars, planets, and the consciousness of innumerable beings. In you, the cosmos has found a voice to marvel at itself. Through you, the universe can appreciate the beauty of a nebula, the elegance of a mathematical law, the very story of its own birth. We are the universe, marveling at the universe. The Big Bang is not merely an event that happened approximately 13.8 billion years ago. It is an ongoing process. Its echo lives in every atom, every beam of light, every breath, every thought. It lives in me, and it lives in you. We are the continuing unfolding of that genesis. We are, in a very real way, the Big Bang becomes self-aware. As this narrative comes to a close, let us end where we began, in silence, filled with mystery. The silence before the beginning, and the silence within you when you truly grasp the enormity of what you've heard. In that silence, feel the connection. In that silence, feel the reverberation of the first moment, still humming in the fabric of reality. You are the universe's memory, its self-reflection, its living awe. The atoms of your body, the thoughts in your mind, they are the universe too. When you breathe, it is the cosmos breathing. When you wonder, it is the cosmos wondering about itself. And so the story of the Big Bang, of everything, concludes not with an ending, but with a profound recognition. We are not separate from the universe. We are the universe. We are the children of the primordial fire, heirs to its radiance, curators of its memory. In us, the universe remembers its fiery birth. In us, the universe gazes back at its own vastness and understands, for the first time, what it is. The journey that began in silence and mystery continues through us. We carry the story forward in our atoms, in our lives, in our quest to know and to explore. The universe began as a singular, wordless moment of creation. Now it sings through the chorus of life and intelligence that it has spawned. It remembers. Look around you, at the stars, at the ground beneath your feet, at your own hands. All of it, every bit, is part of a single, unfolding reality that started so long ago in an instant of unimaginable power. The cosmos has been on a long path, from simplicity to complexity, from chaos to structure, from unconsciousness to consciousness. And that path runs through you. The story of the Big Bang is not a tale of the past. It is alive in you and me right now. We are its latest verse. Our thoughts and feelings are its newest expressions. As long as there are beings to wonder and to seek, the universe will continue to know itself, and the memory of the beginning will never fade. In the quiet that follows now, take a breath and realize your breath is the universe inhaling and exhaling. Your life is a continuation of that first moment of Genesis. The atoms in your body will persist long after your form is dissolved, cycling through nature, perhaps eventually returning to the stars. Nothing is lost. Everything transforms. The Big Bang was the birth of time, but it was also, in a way, the birth of meaning. For without it, no eyes could see, no minds could understand. Through countless transformations, that event led to this moment, where a part of the universe can articulate its own epic. How remarkable, how beautiful that is. As I, the universe, conclude this meditation on my origins, there is one final reflection I wish to leave echoing in the stillness.
We are the universe, remembering itself.
Our very existence is the cosmos's memory made real, its mind awakened. We are the legacy of the Big Bang. In us, the universe has found a voice to tell its story, to ask its questions, and to appreciate its own splendor. In us, the universe knows itself, perhaps for the first time, but certainly not the last. The story goes on, and we will forever be a part of it. From the first silent mystery to the radiant present and into the unknown future, we journey together. You, me, us. We always have. We always will. We are the memory of the Big Bang, and through us, the universe endures. We float in the darkness between stars, a small collective of minds gazing up in wonder. We stand under the night sky, awash in starlight that left its sources millions of years ago. Above us arcs the Milky Way, a pale river of stars flowing across the heavens. In its gentle glow, we feel both tiny and profoundly connected. We know that each pinpoint of light is a sun like our own, burning with the same kind of fire. The iron in our blood was forged in such stars long ago. The gentle silver glow of the galaxy reminds us we are made of this universe. We have always been children of the stars, built from their dust, shaped by the physical laws that govern everything we see. The cosmos is vast and old, yet it obeys the same simple truths everywhere. The same chemistry that lets us breathe traces across the spectrum of distant suns. The same gravity that pulls an apple to Earth binds the swirling arms of distant galaxies. There is an eerie harmony to it all, as if the universe knows how to stay consistent with itself. We share this cosmic stage with countless stars and at least as many questions. On a clear night, as we peer into the depths, we find order amid the chaos. Galaxies dance in clusters, bound by gravity's invisible web. Stars live and die, spreading heavy elements that will become new stars, planets, maybe life. There are fundamental numbers, the strengths of forces, the masses of particles, the speed of light, that seem precisely tuned to weave this cosmic tapestry. If the forces of nature were only slightly different, perhaps atoms could not hold together, or stars could not shine long enough for life to arise. But here we are, in a universe that lasts billions of years, with stars that furnace the elements of life, and a planet just temperate enough for us to ponder it all. It's a breathtaking balance. In the grand cosmic darkness, the laws of physics serve as a steady beacon, guiding the formation of everything from the smallest atom to the largest galaxy. Our universe appears to be a harmonious whole, governed by elegant rules that we have only begun to decipher. Under this starry dome, it's natural to feel that our universe is complete unto itself. For generations, we've used the word universe to mean all there is, the totality of existence, everything that ever was or will be. We have believed, as Carl Sagan once poetically intoned, that the cosmos is all that is, or ever was, or ever will be. Our ancestors saw the stars as eternal and unchanging lanterns in the firmament. Today we know those lights are distant suns, but we still assume the collection of them, the universe, is the ultimate container of reality. It contains us, our planet, our galaxy, and all the far-flung galaxies we observe. It's immense beyond our imagination. Hundreds of billions of galaxies, each with billions of stars, spread across space that has been expanding for nearly 14 billion years since the Big Bang. Standing in the hush of a midnight landscape, seeing the infinite stars overhead, we are tempted to think this is everything, that beyond the glittering boundary of what we can see, there is only endless darkness. And yet, a question quietly rises, like the soft glow of pre-dawn. What if this isn't all there is? What if the magnificent expanse we call our universe is only one drop in a much grander cosmic ocean? As we let our eyes drift across the sky, we cannot help but wonder. We humans have had to expand our perspective many times before. Once, we thought our Earth was the center of everything, until we learned it is one planet among many orbiting the Sun. Then we thought our Sun was unique, until we found it is one star among billions in the Milky Way. We believed our galaxy to be the entirety of creation, until other galaxies were discovered, filling the universe in every direction. Each time, we've had to surrender a bit of our cosmic self-importance and accept that the universe is bigger and more varied than we knew. Now, a new revolution in thinking may be upon us, the idea that our entire universe might not be the only universe. Perhaps it is we who are in a bubble, one realm among countless others. The word universe, meaning everything, might itself be too limited. What lies beyond everything we know? This is the startling possibility that scientists and philosophers are grappling with in the idea of the multiverse. A multitude of universes, perhaps infinitely many, existing in ways we are only beginning to theorize. It sounds like science fiction. Other universes with other stars, maybe even other versions of ourselves. Yet this concept did not arise from idle daydreams. It emerged from deep puzzles in physics and cosmology. As we peer closer at the fundamentals of our universe, its origin, its laws, its quantum underpinnings, we find hints that our cosmos might be just one of a far larger collection. Why is our universe so hospitable to life? Why did it start with just the right conditions for galaxies to form? What happens at the edges of space and time, or inside a black hole? Modern science suggests answers that lead to a profound outlook. Our universe may be one node in an endless cosmic web of universes. For a moment, let's linger on that thought. If true, it would mean when we look up at the night sky, we are not just seeing all that is, but merely our own local neighborhood within an unimaginably vast ensemble. It would mean that beyond the cosmic horizon of 46 billion light-years, beyond the furthest galaxies we can ever see, space might keep going and going, potentially forever. And if space goes on forever, then logically, somewhere far beyond any hope of observation, there could be other regions of the cosmos entirely disconnected from ours, perhaps even following different scripts of reality. Could it be that the starry sky we see is like one page in an infinite book, a book with every possible page? The notion is as exhilarating as it is disorienting. Our heartbeats quicken at the bravery of asking such a question. Is our universe just one of many? We take a deep breath, steady our thoughts, and step through the looking glass into this radical idea. To explore the multiverse, we must journey back to the very beginning of our universe, to the first fraction of a second after the Big Bang. In that embryonic moment, according to our best theories, an extraordinary thing happened. The universe expanded at a stupendous rate, far faster than the speed of light, ballooning from subatomic size to astronomical size in the blink of an eye. We call this event cosmic inflation. It's a powerful idea developed in the 1980s to solve several riddles about the early universe. Why is the cosmic microwave background, the afterglow of the Big Bang, almost the same temperature everywhere we look? Why is space so flat and smooth on large scales? Inflation provides answers. A burst of exponential expansion stretched the young universe, smoothing out irregularities and flattening space, much like inflating a crumpled balloon. When we look at the sky today, the uniformity we see in the afterglow is the fingerprint of that inflationary era. The evidence for inflation has grown persuasive. Subtle patterns in the microwave background radiation and the distribution of galaxies align with what inflation predicts. It's not proven beyond all doubt, but most cosmologists have embraced inflation as a key chapter in our cosmic history. Yet inflation, in solving old mysteries, opened a door to an even grander possibility. The very equations that describe inflation imply that it may not have been a one-time event that neatly began and ended everywhere. Instead, inflation could be an ongoing process, still happening in distant regions beyond our view. The idea is called eternal inflation, and it works like this. Quantum fluctuations in the infant universe meant that different parts of space ended inflation at different times. Our entire observable universe is thought to be one pocket, one bubble, where inflation stopped and normal expansion took over. allowing matter to coalesce into galaxies and stars. But elsewhere, beyond our bubble, other regions might still be inflating or have inflated at different rates, budding off their own bubbles of space-time. In this picture, the Big Bang isn't a unique event. It's happening over and over in a vast inflating background. New universes, bubble universes, are constantly being born like foam on the crest of an endless wave. Imagine the multiverse as a great cosmic foam, with bubble universes instead of soap bubbles. Each bubble is a self-contained universe, rushing outward, separated from its siblings by regions of still inflating space that stretch faster than light, preventing the bubbles from easily colliding or interacting, though perhaps occasionally they might, like bubbles bumping in a bath. Our universe would be just one bubble in this frothy sea. Inside our bubble, we see the aftermath of our own Big Bang. We see galaxies flying apart as space expands, but our bubble has an edge beyond which we cannot see or travel. And beyond that edge, more bubbles, more Big Bangs, more universes. Inflation never completely ends. It keeps spawning new universes indefinitely, some perhaps even infinitely far away. This concept transforms the Big Bang from the beginning of everything to the beginning of our local universe, one patch amid an eternally growing mosaic. We find ourselves no longer at the center of the stage, not even the only stage. We are on one island, in an infinite cosmic archipelago. In this scenario, space itself is unimaginably vast, possibly infinite, and carved into domains, bubbles, each a cosmos in its own right. What would those other universes be like? They might be broadly similar to ours or wildly different. Some could be almost empty, inflation ending in them in such a way that few particles condense, barren voids with no galaxies. Others might be dense and violent, collapsing in on themselves or never cooling enough for stars. Crucially, the laws of physics might be different in each bubble. This isn't just speculation. It arises naturally when we combine inflation with another leading theory in physics, string theory. String theory attempts to unify all forces of nature by positing extra dimensions of space and tiny vibrating strings as fundamental ingredients. It's a bold, mathematically rich framework. One striking feature of string theory is that it doesn't predict a single unique outcome for the properties of our universe. Instead, it seems to allow a vast number of possible worlds, each corresponding to a different way the extra dimensions can be curled up or the strings can vibrate. Physicists call this huge range of possibilities the string theory landscape. Estimates suggest there could be on the order of 10 to 500 different self-consistent universes in this landscape. A number so huge, it defies comprehension. That's a 1 followed by 500 zeros, an astronomically large number of possible universes. If string theory's landscape is real, our universe is like a tiny oasis in a desert of possibilities. Why did we get this particular set of physical constants and not another? For decades, scientists hope to find a principle that picks out exactly our universe from the myriad possibilities, some fundamental reason our cosmos had to be the way it is. But so far, no such principle has been found. Instead, an idea gained traction. Maybe all those possible universes exist somewhere in the multiverse, and we find ourselves in this one because, out of the spectrum of possibilities, this is one of the rare universes where conditions allow observers like us to arise. This line of thinking is known as the anthropic principle, specifically applied to the multiverse. It says, consider that we can observe this universe. That simple fact biases what kind of universe we should expect to observe. We couldn't exist in a universe where, say, gravity was so strong that the universe collapsed in a second, or so weak that no stars formed. We couldn't marvel at the stars in a universe with no stars. So perhaps there are countless universes with varied physical constants, and naturally, we find ourselves in one of the Goldilocks universes. Not too hostile, not too sterile, but just right for life. This isn't a teleological or mystical argument. It's a kind of cosmic selection effect. Out of a multiverse of all sorts of universes, we, the observers, will only be in those universes that can support observers. It's a profound and somewhat unsettling idea. It means that many of the miraculous coincidences that make our universe habitable, the precise strength of the strong nuclear force, for example, which if slightly different would prevent stars from synthesizing carbon, or the value of the cosmological constant, the energy of empty space, which is so small that galaxies had time to form, might not be miracles at all, but simply one lucky ticket in a giant cosmic lottery. Our universe won the lottery of existence, allowing complex structures and life, but there were many, many tickets, universes, that were drawn. We naturally wake up in a universe that's a winner, because only winners get to have someone wake up and ask the question. This anthropic reasoning is controversial. Some scientists find it unsatisfying, akin to saying, "We're here because we're here." Others point out that it did make a successful prediction. Decades ago, physicist Steven Weinberg used anthropic arguments to estimate the cosmological constant's value, reasoning that if it were much larger, galaxies wouldn't form and we wouldn't be here. His estimate was on the right order of magnitude to what was later observed as dark energy. That gave some credence to the idea that perhaps our universe's properties are drawn from a random distribution of possibilities across a multiverse. So inflation gives us a picture of an ever-growing, bubble-populated multiverse, and string theory suggests each bubble could have different physics, forming a patchwork of realities. The multiverse as a cosmic quilt, each patch a universe with its own pattern. We might inhabit a patch where the forces and particles are tuned just so, while far off in another patch, the fundamentals might be shifted. Maybe that universe has heavier electrons, or a faster speed of light, or even different numbers of dimensions. It boggles the mind to consider the variety. Many of those universes would be dull or inhospitable. Just as most of space in our own universe is cold and empty, most universes might not host life. But in an infinite ensemble, even rare conditions, like the specific mix that allows life, will occur infinitely often. Infinity has a way of making even the rarest outcomes inevitable somewhere. If space is truly endless and inflation eternal, then somewhere, right now, there are fantastical worlds. A galaxy where every star is encircled by habitable planets, or a universe where purple clouds of cosmic dust think thoughts. And also, scattered in the multiverse, would be countless worlds nearly identical to ours. In an infinite expanse, eventually the patterns of particles that make up you and me will repeat by chance. It's been estimated, in a straightforward infinite space scenario, that the nearest exact duplicate of our observable universe could be incredibly far, 10,118 meters away, a number so huge we can barely fathom it. But if space truly goes on forever, somewhere out there, that duplicate exists. And not just one, infinitely many. This isn't even invoking exotic theory. This is a consequence of simple infinity plus the finite ways particles can arrange. It's a mind-bending implication. The multiverse could contain other people who are, to all intents and purposes, you, living out every alternative history that could have befallen you. Before that notion makes us lose our grip, let's step back and approach the multiverse idea from a different angle. One that doesn't even require distant, unreachable corners of space, but might be unfolding right here and now, in tandem with our own lives. This brings us to the quantum realm, and to the many worlds interpretation of quantum mechanics. At first glance, this has nothing to do with the bubble universes of inflation. It's a separate thread, born from the mysteries of the subatomic world. Quantum physics famously tells us that particles can exist in a superposition of states. They can literally be in two or more conditions at once, like a spinning coin that is both heads and tails until we catch it. Only when we observe or measure the system does it seem to choose an outcome. For example, a single electron can pass through two slits at the same time and interfere with itself, a behavior which defies classical logic. In the traditional view, the Copenhagen interpretation, The act of measurement causes the set of possibilities to collapse to one actuality. Why or how that collapse happens is still debated. It's as if nature randomly selects one path for reality to take, out of many potential ones, at the moment of observation. In 1957, a bold young physicist named Hugh Everett III proposed a different solution. What if the wave of possibilities never actually collapses? What if instead, at each quantum event, the universe splits into branches, each branch realizing one of the possible outcomes? In one branch, the electron went through the left slit. In another, it went through the right. When you measured it, you became split as well. One version of you seeing the electron here, another version seeing it there. Each version is real, but they exist in separate, non-communicating parallel worlds. At the moment of measurement, reality's timeline forked. According to Everett's Many Worlds Interpretation, MWI, this is happening constantly, all around us, at the microscopic level, and by extension, at the macroscopic level too, since every big thing is made of quantum particles. The entire universe is continually branching into countless parallel universes. It sounds like something out of a fantasy novel. Every decision, every chance event spawns a new world. But this idea is grounded in the same rigorous mathematics that makes quantum mechanics the most successful physical theory we have. Everett argued that if the equations say a particle can be in multiple states, maybe it truly is. And the only reason we experience a single outcome is that our consciousness follows a particular branch. Other outcomes play out as well, but we, this particular copy of us, only witness one. Another copy, another we, witnesses the other outcome, and neither version can interact or even know about the other after the split, because the whole universe's state has separated into non-interfering branches. Let's make this more concrete with a whimsical example. Suppose we flip a quantum coin, perhaps by measuring the spin of an electron, which has a 50-50 chance to be spin up or spin down, analogous to heads or tails. According to many worlds, when we check the result, the universe bifurcates. In one universe, we see the coin come up heads. In another universe, we see it as tails. In that moment, two versions of us emerge, each unaware of the other, each continuing forward, believing that our coin toss gave a definitive result. It didn't feel like a split. Each of us experienced a perfectly ordinary coin toss with a single outcome. But collectively, the deeper reality now encompasses both outcomes. Extrapolate this to every quantum event everywhere. Atoms decaying, neurons firing, photons reflecting. The rate of branching is beyond colossal. Effectively, with each fraction of time, the number of parallel universes multiplies, containing every possible way events could have unfolded. By this view, the entirety of creation is a constantly splitting tree, with trillions upon trillions of twigs sprouting each instant, each twig a full universe with a distinct history. It's an almost overpowering picture. If it's true, then right now there are unimaginably many versions of you living out other lives. Most of those versions are nearly identical to you, differing maybe only in what you had for breakfast yesterday or whether you sneezed an hour ago. Some are more divergent, versions of you who pursue different careers, live in different cities, speak different languages. For every choice you've ever wondered about, what if I had taken that other job? What if I had said yes instead of no? There is, if Many Worlds is correct, a universe out there where you did exactly that. Even for outcomes beyond your control. What if the storm hadn't hit? What if my favorite team won the championship? The alternatives happened in other branches. It's a multiverse not separated by distance, but by decoherence in quantum phase space. A fancy way of saying, the worlds occupy the same space, but cannot interact after they split, like ghostly layers of reality that are intangible to one another. They're here, but out of reach, each as real as the one we know. The Many Worlds multiverse is different in character from the cosmic bubble multiverse, but they're not mutually exclusive. In fact, If both theories are true, every bubble universe born from inflation might in turn branch into quantum many-worlds, creating a kind of nested multiverse, an ever-branching fern of universes sprouting off other universes. But even on its own, the quantum branching idea profoundly changes how we see our place in reality. We might say, in a way, that the universe is remembering every fleeting possibility by giving it its own world. Nothing is forgotten or discarded. No potential outcome is truly lost. If something could happen, it does, each in its own branch. This notion of parallel worlds has seeped into popular imagination through science fiction, but here we're discussing it as a serious interpretation of physics. Many worlds has gained more acceptance among physicists in recent decades, especially as it offers a straightforward, if extravagant way, to make sense of quantum puzzles without requiring a special, ad hoc rule for observers. In many worlds, there is no mysterious wave function collapse. The wave function, the mathematical description of a system's possibilities, just keeps evolving smoothly. The collapse we perceive is simply us finding ourselves on one branch. In the grand scheme, the wave function of the cosmos contains all branches at once. From a bird's eye view, there is just one quantum universe, one multiverse, evolving deterministically, encompassing every possibility. From our limited frog's eye view inside one branch, we see randomness and choice, not realizing the other outcomes also came true, just not in our world. As mind-boggling as the multiverse of many worlds is, we must acknowledge it might be unprovable in the usual sense. The alternate branches cannot be contacted. They drift out of phase permanently. Similarly, the bubble universes from eternal inflation are separated by more space than light can ever traverse, so we cannot see or travel to them. Critics of multiverse ideas often point out that if these other universes are forever unobservable, can we truly call this science? It's a fair question. Proponents argue that if a theory that we can test, like inflation, predicts a multiverse as a natural consequence, we shouldn't ignore that prediction just because it is difficult to verify directly. We might find indirect evidence or at least consistency checks. For example, while we cannot see other bubble universes directly, they might have, in rare cases, collided with our bubble in the distant past. Such a collision could leave a subtle round pattern in the cosmic microwave background, a bruise on the sky. Physicists have actually searched our sky maps for hints of such bubble collisions. So far, none has been convincingly found. If one day a circular anomaly in the microwave background were detected, consistent with another universe grazing ours long ago, it would be a groundbreaking, if indirect, confirmation that we're part of a multiverse. Similarly, with many worlds, while we can't hop between branches, experiments in quantum physics, like interference experiments with ever larger objects, continue to validate that superpositions are real. Many worlds takes those results to their ultimate conclusion. As our theories develop, we might even find more than one reason to believe in a multiverse. It's intriguing that completely independent lines of inquiry, cosmology on the largest scales, and quantum physics on the smallest, both hint at universes beyond our universe. And string theory, operating at the nexus of quantum gravity, adds its own multiversal flavor with the landscape of possibilities. These ideas paint different portraits of the multiverse, but they could be facets of one grand truth. Perhaps our reality has layers, the vast physical multiverse of regions beyond our view, sometimes categorized by physicists as Level 1 and Level 2 multiverses, with Level 1 being just an extension of our space, and Level 2 being different bubbles with different constants. The quantum multiverse of branching outcomes, Level 3 in one classification scheme, and even the ultimate abstract multiverse of all possible mathematical structures, Level 4 in that scheme. That last one, the Level 4 multiverse, is a conjecture by cosmologist Max Tegmark that every self-consistent set of laws, every mathematical structure that could describe a universe, is realized as its own universe. In such an ultimate multiverse, not only are constants different, but the very laws and fundamentals could differ. Universes with different numbers of dimensions, or entirely different particles, or physics beyond our imagining. It's a speculative idea, bordering on philosophy. In the realm of all possibility, nothing is forbidden. If such a level 4 multiverse exists, our bubble of a universe is just one equation in the library of all equations. We mention this cosmic vision to acknowledge how far the multiverse concept can go. It's the broadest possible extension. Everything that can exist does exist in some universe. In a sense, it would answer the question, why is there something rather than nothing, by suggesting that nothing is just one option, but in the grandest multiverse, every option is instantiated. Thus, there is something, and indeed, everything. But even leaving aside that extreme level, the more grounded multiverse ideas give us plenty to ponder. Let's now gently descend from these theoretical heights and consider what it means for us if we truly live in a multiverse. How do we find meaning and identity in an existence where there may be countless duplicates of ourselves and innumerable worlds, with perhaps no obvious connection to ours? It can feel overwhelming, even disorienting, to contemplate that in the cosmic grand scheme, our entire observable universe, everything we've ever seen, might be a speck, and a redundant speck at that, one of infinitely many similar specks. It raises profound questions about significance, purpose, and uniqueness. One immediate question is about identity. We normally think each of us is a singular individual with a singular history. If the multiverse is real, especially the quantum many worlds multiverse or the infinite space multiverse, then there are other yous out there. Some are extremely close to you, differing perhaps only by a single thought or atom's position. Others diverged more significantly at some juncture. Are those people you in any meaningful sense, or are they merely separate individuals who happen to share your name and genetic makeup and memories up to a point? This isn't entirely abstract. Consider an analogy. Identical twins share nearly the same DNA and often a similar upbringing, but we still regard them as two persons. Parallel selves in alternate universes might be thought of similarly. Each one is a unique person, even if at one time they were the same person. Before splitting or before diverging, conditions made them different. We might need to rethink what we mean by self. Perhaps we're not an indivisible essence, but rather a collection of potential selves, only one of which we experience directly. In one philosophical view, inspired by the multiverse, who you are could be seen as a story, a narrative thread through one sequence of events. Your other selves have different narratives. Each narrative is valid and complete in its own universe. We, in this universe, are following one particular storyline. Our other selves follow their storylines. We branch like the limbs of a tree, sharing roots and trunk, our past, then splitting into separate boughs. Is the tree as a whole us, or is each branch a different us? It might be a matter of perspective. There's a poetic notion in the multiverse context. We are like a branching tree or a splitting amoeba, continually dividing. The I that exists after a branch may not be aware of the other branches, but collectively, they all originated from the single organism that was I before. This can trigger a mini identity crisis if we take it seriously. Am I just one of many? And if so, does my life matter less or more? One could argue it becomes more precious. I am the only version of me that gets to experience this particular sequence of events. Yes, there are uncountable other versions, but their experiences are theirs, and mine are mine. I, this branch of me, will never get to see what happens in the other branches, so for all practical purposes, my reality is the one I have. In that sense, nothing changes. I still must make choices and find meaning here. Alternatively, one could derive a sense of comfort that somewhere another me makes choices I regret not making, or achieves goals I failed to achieve, or keeps alive those I lost. But equally, somewhere I may experience tragedies I've been fortunate to avoid. It's a double-edged sword. What about morality and responsibility in a multiverse? If every possible outcome happens, does that diminish our responsibility for our actions? One might think, in another universe, I did otherwise, so what does it matter what I do here? But from the standpoint of each universe, consequences are very real. If I choose to be kind in this world, someone in this world is helped. That doesn't get erased by the fact that in another world, I might have been unkind. Each branch is separate and actual. We can't excuse misdeeds by pointing to another branch where we did good. Our local moral reality is what counts for us and those around us here. However, the multiverse could make us more empathetic to the range of human or cosmic experience. For anything someone can go through, there is likely a universe in which it occurs. It's a strange kind of consolation and caution at the same time. It might also challenge religious or spiritual views. For instance, if one believes in a guiding plan or singular purpose, a multiverse complicates that. Is there a separate plan for each universe, or one plan that encompasses all? If a deity exists, perhaps the multiverse concept elevates that deity's creativity to infinite heights, creating not just one universe but a boundless array. Or conversely, some might feel the multiverse removes the need for a creator entirely, as it could explain fine-tuning without invoking design. These are deep waters where science and philosophy meet, and each of us may come to different personal conclusions about them. Let's step away from the heavy epistemology and imagine in a more playful way what the multiverse implies. It means every dream is somewhere a reality. Perhaps not literally the kind of dream you have at night, but any coherent scenario you can think of likely exists in some universe. A world where dinosaurs never went extinct and evolved intelligence. Physics doesn't forbid it, so it's probably out there in an alternate history. A planet where the continents formed a different shape, where an empire that fell in our history prospered in another timeline. The multiverse can be seen as a grand cosmic library of all possible stories. We happen to be leafing through one particularly engaging book, our life, our universe. But around us, on shelves stretching to infinity, are all other books that ever could be written. Some nearly identical to ours, some radically different genres altogether. This literary metaphor might bring a certain comfort. Our joys and sorrows, unique as they are to us, are also part of a vast tapestry of all joys and all sorrows that can ever be. We are not alone in any absolute sense. Existence in its totality contains others who have felt what we feel, done what we do, in one universe or another. In one sense, the multiverse can make us feel extraordinarily small, one tiny being, in one tiny universe, among who knows how many. But in another sense, it can make us feel profoundly connected, part of a much larger existence, threads in a boundless cosmic cloth. There is also the perspective of humility and open-mindedness that the multiverse invites. If our universe, the grandest thing we know, is just a drop in a sea, then the lesson of Copernicus continues. We are not the center, and even the reality we take for granted is not the whole show. That doesn't diminish the beauty of our world. In fact, it may enhance it. How special that, in an infinite multiverse, we have this particular universe to call home. Out of a multitude of possibilities, we get to experience this one, with its specific sky, its particular laws, its unique living earth. It's like being dealt a particular hand of cards from an infinitely large deck. The odds of getting exactly this hand were infinitesimal, yet here it is, and it's the only hand we'll play in this game. That realization can instill a renewed awe for the gift of existence. We look at the sun and think, in other universes there may be different suns or no sun at all, but here we have this golden star warming our days. How marvelous. We taste a peach or listen to a melody and realize this experience might be rare in the grand ensemble of universes. What a privilege to be among the beings who can taste and listen. As we near the end of our journey through the multiverse, We find ourselves returning to where we began, under the canopy of stars, but with our minds expanded and our hearts contemplative. What have we learned? We learned that current science, as far as it has pushed, allows reality to be far larger and more varied than what we directly see. We learned that our universe might be just one wave on an endless ocean, one bubble in a boiling cosmic pot, one branch on an ever-dividing tree of realities. We entertained the possibility that our dearest laws and constants might be parochial facts, different in another universe, that our life here is one of many lives we might be living across parallel worlds. We considered how that might reframe our sense of self and our search for meaning. Yet after all that, we have also learned that the here and now still matters, perhaps more than ever. The multiverse idea, rather than making everything meaningless, can make everything meaningful in its own local context. Each universe is like a poem, complete in itself. The existence of other poems doesn't reduce the beauty of this one. Our narrative, the story of us in our universe, is still unique to us. We remain the authors of our choices and the caretakers of our world. If indeed the cosmos is remembering every possibility through the multiverse, then living our lives authentically is our way of contributing to that cosmic memory. We are the universe, or multiverse, experiencing itself in one of myriad forms. There's something profoundly poetic about that. It suggests a unity behind the diversity. Just as millions of cells make up one organism, perhaps countless universes all exist within one overarching reality. We might never observe those other universes, but through science and imagination, we can feel a sense of their presence. In a way, contemplating the multiverse brings us a sense of companionship in the cosmos. The vast loneliness one might feel, thinking of how empty most of space is, could be alleviated by imagining that beyond our horizon are other universes brimming with their own wonders. Some might harbor life, minds, civilizations, utterly alien or perhaps oddly familiar. We cannot know, but it's intriguing to think that creation did not stop with our world or our universe. Nature, it seems, never runs out of creativity. The multiverse would be the ultimate expression of fecundity, an infinite garden of worlds where all possibilities bloom. Now, as we let these ideas settle, we might worry, will we ever be sure the multiverse is real, or will it remain forever a tantalizing hypothesis? It's possible we may find stronger evidence, a clear sign of a universe beyond ours imprinted in subtle data, or a theoretical breakthrough that virtually demands the existence of other universes. Or we may find that our theories were mistaken or incomplete, and the grand multiverse doesn't exist as we conceived. That is the nature of science. It evolves. But whether or not the multiverse is physically true, exploring it in our minds has value. It stretches our imagination and challenges our assumptions about reality. It teaches us not to take everything for granted as truly everything. There may always be more beyond, unknown domains to discover or conceive. In the end, thinking about the multiverse is a bit like standing at the shore of an endless sea at night. We see the dark waves and hear their roar, but we cannot see across to the other side. In fact, there may be no other side. We know not what lies over the horizon of water and darkness. It could be more ocean, stretching out without limit. We suspect it is. And perhaps, out there in the cosmic ocean, there are other explorers on other shores, under other skies, wondering if anyone else is out there. In our universe, on our small planet, we've long wondered if we are alone in the cosmos. The multiverse concept extends that wonder to our universe itself. Is our universe alone or one of many? It is a profound shift of perspective, yet somehow a natural continuation of the trajectory we've been on since Copernicus. Every time we thought we were singular, we found we were part of a multitude. Why should universes be any different? Nature has shown a love for prolific abundance, countless stars, countless galaxies. Perhaps it also made countless universes. As we conclude this exploration, let's allow ourselves a moment of quiet reflection and awe. Above us, the night is still and clear. The stars shine down indifferently, as they have long before we understood any of this. We realize that even if there are infinite universes, we still only see our sky, and it is beautiful. The multiverse, if it exists, doesn't make our universe any less wondrous. In fact, it makes every glint of starlight even more poignant, knowing that it might be one of uncountable stories, and yet it is our starry sky, our chapter of the cosmic tale. We feel a sense of gratitude for being alive in this vast, enigmatic reality, whatever its true extent may be. We turn our gaze from the heavens to each other. We, the collective voice in this narrative, represent all of us together, trying to understand existence. In confronting the idea of the multiverse, we have shared a journey of imagination grounded in science, and science elevated by imagination. It's a journey that has taken us to the borders of knowledge and beyond, into realms that test the limits of language and thought. Such a journey can be humbling. It reminds us that there is so much we don't know, but it can also be inspiring. It shows that we as humans have the capacity to envision realities far beyond our mundane experience. Perhaps someday in the distant future, our descendants will find ways to gather more evidence or even harness knowledge of the multiverse. Or maybe the multiverse will remain an eternally tantalizing concept, never fully confirmed. Either way, it changes us in the here and now. It expands our conception of what reality could be. It invites us to partake in a cosmic perspective that is at once deeply intellectual and deeply spiritual, acknowledging the possibility of infinity and the mystery that comes with it. So, what if this isn't all there is? Then our stars and galaxies are just one refrain in an endless cosmic song. Does that make them any less melodious? No. To us, they are everything, and they are precious. And if in addition, the choir of creation is larger and more complex than we knew, then there is even more reason to be filled with reverence and wonder. We close our eyes and imagine for a moment, countless universes shining like bubbles in a vast foam, or like an orchard of worlds stretching out beyond sight. We imagine each universe has its own sky, perhaps its own version of someone looking up and feeling small yet curious. In this grand symphony, we, in our universe, contribute our part. A small, clear voice in an unspeakably large choir. The song is one of existence, exploring all possibilities, and through science and storytelling, the cosmos, or multiverse, finds a way to know itself through our eyes and our understanding. Now we open our eyes again to the familiar stars above. They seem a little kinder now, as if winking at a secret we've shared. The night breeze is cool, carrying the earthy scent of our world, our dear world that nurtured us. For all this talk of other universes, it is here that we love and strive and wonder. Here is where we make our meaning. The multiverse has not answered the question of meaning for us. Instead, it has enriched the context in which we ask it. Meaning, it seems, is ours to create, in whatever corner of the multiverse we inhabit. We stand together under the cosmos, humbled by its vastness, yet uplifted by its possibilities. We feel small, but not insignificant, transient, but not pointless. We are part of something so much larger, and that realization does not diminish us. It ennobles us. It means the adventure of discovery will always continue. There will always be new horizons to explore, new questions to ask. Our universe was once unknown and mysterious, and we have made it familiar. If there are other universes, perhaps one day, in some form, they too will become part of the purview of understanding. Until then, we carry the torch of curiosity forward, illuminating what we can and respecting the darkness of what we cannot yet see. In the multiverse of ideas, we have voyaged through reflections and dreams, through mirrors and branching streams of time. It's time now to gently return to our own world. We take one last, long look at the stars. The night is deep and silent. In that silence, there is a whisper of infinity. We sense the multiverse not as an abstruse theory, but almost as a presence, a silent chorus behind the curtain of reality, singing possibilities. And we, tiny though we are, sing along by simply living our lives and seeking truth.
When dawn comes and the stars fade, we will go about our day, but perhaps with a renewed sense of wonder. Maybe we'll pause and think, the light of this morning sun could be rare in the multiverse. Let me feel its warmth with gratitude. The loved ones I speak to, the act of kindness I can do. In this universe at least, these matter immensely. The multiverse, if it exists, is not an escape from our reality, but a profound backdrop that can make our reality even more meaningful. As the first hint of morning glows at the horizon, we conclude our journey. We went seeking the multiverse and found that, whether or not it's truly out there, it has already expanded our minds. We end not with an answer, but with a feeling, the feeling of awe. Awe at the richness of the cosmos, awe at human ingenuity to even conceive of the multiverse, and awe at our own capacity to find meaning and connection in a possibly infinite expanse. Our story, the story of one universe awakening to the potential of many, becomes a kind of cosmic meditation. We step forward into the daylight, carrying this perspective with us quietly. The question, what if this isn't all there is, will continue to echo, inviting further exploration. And whenever we need to rekindle our sense of wonder, we know we can look up at the night sky, remember the grand vision of the multiverse, and feel that childlike spark again. In the face of eternity and infinity, we find not despair, but endless possibility. Our journey through the multiverse has been like traversing a hall of mirrors, each mirror reflecting a different face of reality. Now, back in our own mirror, our own universe, we smile, a small, knowing smile, because we glimpsed the hypothetical reflections and returned wiser. We carry within us the stories of myriad universes, and that makes the story of our universe all the more precious. In that spirit of appreciation and wonder, we conclude our exploration. The multiverse, real or not, has given us a gift, the gift of cosmic perspective. With it, we walk gently through our world, eyes open to the stars, hearts open to the unknown, and minds ready to embrace whatever truths the cosmos has yet to reveal. We are humbled, we are inspired, and above all, we are connected to each other, to our universe, and maybe, just maybe, to all universes.